Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, where distant corners of the universe become a little easier to understand, and where science takes its time. Tonight, we're setting our sights on something remarkably small, by cosmic standards, yet surprisingly difficult to explain. Our destination is a galaxy called I Zwicky 18. Now, galaxies are usually ancient things. They're among the oldest structures in existence, vast collections of stars that have spent billions upon billions of years growing, changing, colliding and evolving. Most galaxies have histories so long that even trying to imagine them can feel exhausting. Entire mountain ranges on Earth have risen and vanished while those galaxies quietly continued their journey through the cosmos. Yet somewhere out there is a galaxy that made astronomers stop and ask a very unusual question. What if this one is different? What if, among all the ancient cities of stars scattered throughout the universe, we had somehow discovered one that seemed almost young? Not merely young compared to another galaxy, young compared to nearly everything. Before we settle into that mystery, I'd like to ask you something. Where are you listening from tonight? Perhaps you're tucked into bed after a long day. Maybe you're relaxing on a sofa with a blanket nearby. It could even be morning where you are, with sunlight beginning to creep through a window. And while you're considering that, here's another fitting question. How old does something need to be before we call it ancient? 100 years? 1,000? 1,000,000? The universe, after all, has a way of making our usual definitions seem rather modest. If you find these sleepy journeys relaxing, interesting, or simply helpful at the end of a busy day, I'd be grateful if you gave the video a like and subscribed. It helps this little corner of calm science find more curious listeners who enjoy falling asleep somewhere between astronomy and imagination. Now, get comfortable. There's no rush tonight. The galaxy we're visiting has waited a very long time for attention. A few more moments won't hurt. To understand why I Zwicky 18 became so famous, we need to begin with a simple expectation. Astronomers generally assume that galaxies are old, very old. Not because they're stubborn or attached to tradition, but because the evidence points strongly in that direction. The universe itself is approximately 13.8 billion years old. Not long after the Big Bang, matter began gathering into larger structures. Tiny fluctuations in density slowly grew under gravity's influence. Clouds of gas condensed. The first stars ignited. Eventually galaxies emerged. Some remained small, others became giants. Many merged with neighbours, many changed shape, all accumulated stories. By the time humanity appeared on Earth, galaxies had already existed for billions of years. In a sense, every galaxy we observe today is a survivor. Each one carries the marks of an incredibly long history. That's why astronomers often think of galaxies as cosmic archives. Every generation of stars leaves clues behind. Stars manufacture heavier elements. When those stars die, they release those elements into surrounding space. New stars then form from that enriched material. The process repeats, again, and again, and again. Over time, galaxies become increasingly chemically complex. Like a city adding new buildings over centuries, every generation leaves evidence that it was there. This means astronomers can often estimate a galaxy's history by examining what it's made of. A galaxy rich in heavy elements usually has experienced many generations of star formation. A galaxy lacking those elements may tell a very different story. At least that's what researchers suspected. For much of the 20th century, astronomers gradually mapped more and more galaxies. Some were elegant spirals, some were giant ellipticals. Others looked irregular, almost chaotic. The universe seemed wonderfully diverse, but one assumption remained fairly secure. Galaxies were ancient structures. Then I Zwicky 18 arrived and complicated everything. Its name isn't particularly poetic. Astronomers unfortunately have a habit of assigning labels that sound more like filing cabinet entries than cosmic wonders. I Zwicky 18 was named after the astronomer who catalogued it, a remarkable scientist called Zwicky. Zwicky himself was a fascinating character. Brilliant, outspoken, and occasionally intimidating, he contributed to several major discoveries in astronomy. Long before dark matter became a household term among science enthusiasts, Zwicky was already arguing that something invisible seemed to influence galaxies. Many of his ideas were far ahead of their time. One of the galaxies catalogued through surveys connected to his work eventually became known as I Zwicky 18. At first glance, it doesn't look particularly impressive. It isn't enormous, it isn't spectacularly bright. It lacks the grand spiral arms that make some galaxies famous. If galaxies were cities, I Zwicky 18 would not resemble a glittering metropolis. It would look more like a distant, isolated town. Yet appearances can be deceiving. Astronomers eventually noticed something strange. The galaxy seemed unusually blue. Now, blue might not sound like an alarming colour for a galaxy, but in astronomy, colour tells stories. Young, massive stars burn extremely hot. Hot stars often appear blue-white. Older stellar populations tend to produce redder light. Therefore, a galaxy dominated by blue light suggests vigorous recent star formation. In simple terms, lots of relatively young stars. That alone wasn't shocking. Many galaxies form new stars. The real surprise emerged when astronomers examined the galaxy's chemistry. Remember those heavier elements produced by generations of stars? Researchers found remarkably small amounts of them. The galaxy appeared chemically primitive, almost untouched, almost inexperienced, almost as though countless cycles of stellar evolution had never happened. Imagine walking into a supposedly ancient city and discovering almost no signs of previous generations. No old foundations, no ancient roads, no historical layers, just a surprisingly fresh landscape. That's roughly how unusual the observations seemed. Naturally, astronomers became interested. Actually, interested might be too mild a word. Some became excited. Others became skeptical. Many became both simultaneously. After all, extraordinary claims require extraordinary evidence. If I Zwicky 18 truly contained only young stars, the implications would be enormous. Galaxies were supposed to have formed near the beginning of cosmic history. Finding one that appeared genuinely young in the nearby universe would be astonishing. It would be a bit like discovering a newborn forest growing in the middle of a continent where every other forest was ancient. The question wasn't merely whether the galaxy looked young. The question was whether it actually was young. Those are not always the same thing. As astronomers gathered more observations, the mystery deepened. The galaxy sits roughly 59 million light-years away from Earth. That distance sounds immense because it is immense. Light leaving the galaxy began its journey long before humans invented agriculture. Long before pyramids, long before written language. Yet in astronomical terms, 59 million light-years is relatively nearby. There are galaxies billions of light-years farther away. Compared to those remote objects, I Zwicky 18 resides almost in our cosmic neighbourhood. That proximity made the puzzle even more intriguing. If the galaxy really was young, why was it nearby? Why hadn't it formed alongside most other galaxies billions of years ago? Why would galaxy formation apparently occur so late in cosmic history? Questions multiplied. Answers remained elusive. Part of the challenge came from the galaxy's size. I Zwicky 18 belongs to a category known as dwarf galaxies. Dwarf galaxies contain far fewer stars than giants like our own galaxy, the Milky Way. The Milky Way contains hundreds of billions of stars. I Zwicky 18 possesses only a tiny fraction of that population. Small galaxies are important because many astronomers believe they resemble some of the earliest building blocks of larger galaxies. Studying them can reveal clues about conditions in the young universe. In that sense, dwarf galaxies function almost like fossils. Not literal fossils, of course. Nobody's brushing dust from ancient stars with tiny archaeological tools. But they preserve information from earlier eras of cosmic history. Some dwarf galaxies appear relatively unchanged compared to larger systems, that have undergone countless mergers and transformations. If I Zwicky 18 truly represented a young galaxy, it could provide a rare opportunity. Instead of observing distant galaxies near the dawn of cosmic history, astronomers might have a nearby example they could examine in extraordinary detail. That possibility was irresistible. Telescopes around the world and in space gradually turned their attention toward this peculiar object. Researchers analysed its light, measured its composition, compared it with theoretical models, debated interpretations, published papers, published responses to papers, published responses to responses, which in fairness is often how science progresses. Science is not a straight road. It resembles a conversation stretching across decades. One group proposes an explanation, another group challenges it. New evidence arrives, old assumptions are revised. Sometimes conclusions survive, sometimes they don't. The important thing is following the evidence wherever it leads, and in the case of I Zwicky 18, the evidence was leading somewhere unexpected. Many observations pointed toward extreme youthfulness. The galaxy contained very little of what astronomers call metals. In astronomy, the word metal means almost anything heavier than hydrogen or helium. Carbon counts, oxygen counts, iron counts. The terminology is wonderfully convenient for astronomers and occasionally confusing for everyone else. The early universe consisted primarily of hydrogen and helium. Heavier elements emerged later inside stars. Therefore, a galaxy with extremely low metallicity appears chemically closer to the early universe. I Zwicky 18 possessed one of the lowest metallicities ever measured in a galaxy. That immediately made it special. It seemed less evolved than expected, less processed, less altered by generations of stellar activity. For a while, some astronomers wondered whether they might be seeing something extraordinarily rare, a galaxy that had somehow delayed significant star formation until relatively recently. Imagine a cosmic community where nearly every resident had lived there for billions of years. Then one newcomer arrives. Naturally, everyone wants introductions. The galaxy became famous not because it provided answers, but because it generated questions. Questions are often more valuable. Answers can end discussions. Questions create new discoveries. As years passed, increasingly powerful instruments became available. Astronomers gained sharper views than ever before, and those improved observations would eventually reveal details hidden from earlier studies. But before we reach those discoveries, it's worth appreciating how unusual the situation already was. Most famous astronomical objects become famous because they're enormous, or bright, or violent, or dramatically beautiful. I Zwicky 18 became famous because it seemed out of place. Its significance emerged from contrast. Everything about it appeared to challenge expectations. The galaxy was quietly asking whether astronomers truly understood how galaxies age, whether chemical composition always tells a straightforward story, whether appearances can deceive even the most sophisticated observers. Those questions transformed an obscure dwarf galaxy into one of the most discussed small galaxies in astronomy. And perhaps the most fascinating part is that the mystery wasn't simply about one object. It was about time itself. Not the philosophical kind. Not the kind discussed by clocks and calendars. Cosmic time. The timeline of galaxy formation. The story of how structure emerged from an expanding universe. Because if a genuinely young galaxy existed nearby, then perhaps the universe still had surprises hidden among its billions of stars. Perhaps some corners of space followed different schedules. Perhaps galaxy evolution was more complicated than anyone realized. Astronomers needed better evidence, better measurements, better ways of determining a galaxy's age, and that meant turning to one of the most powerful tools ever built for exploring the universe. A telescope that would eventually peer deep enough into I Zwicky 18 to search for something that could settle the debate once and for all. Not bright gas clouds, not chemical signatures, not theoretical predictions, but stars. Very old stars. If they were there, they would change everything, and if they weren't, the implications would be even more remarkable. A great many discoveries in astronomy begin with something spectacular, a brilliant explosion, a gigantic collision, a dazzling object shining across unimaginable distances. I Zwicky 18 was not one of those discoveries. In fact, if you were casually browsing through images of galaxies, there's a good chance you would scroll right past it without giving it much thought. It lacks the elegant spiral arms that make galaxies like the Milky Way or Andromeda Galaxy instantly recognizable. It doesn't possess the enormous size of giant elliptical galaxies. It isn't surrounded by dramatic rings, enormous jets, or other features that typically attract attention. At first glance, it looks modest, small, irregular, almost unfinished, yet appearances can be remarkably deceptive in astronomy. Sometimes the most ordinary-looking objects end up causing the biggest headaches. That was certainly true here. The story begins during a period when astronomers were cataloguing vast numbers of galaxies. Throughout the 20th century, improvements in telescopes allowed researchers to identify more and more distant objects. What once appeared as faint, fuzzy patches through a telescope slowly transformed into recognizable galaxies, each containing millions or billions of stars. Astronomers love catalogues. Perhaps not in the same way children love birthday presents or adults love finding forgotten money in an old coat pocket. But there is a special satisfaction in organising the universe into lists. Every newly identified galaxy received a designation. Most of those designations were practical rather than poetic. I Zwicky 18 was one of them. The name traces back to the work of the astronomer Fritz Zwicky, who spent years surveying the sky and identifying countless objects. At the time, nobody suspected that this small galaxy would eventually become one of the most discussed dwarf galaxies in modern astronomy. Initially, it was simply another entry in a catalogue. Astronomy is full of such entries. Most never become famous. Some do, and occasionally one becomes famous for reasons nobody expected. As telescopes improved and researchers began studying individual galaxies in greater detail, I Zwicky 18 gradually attracted attention. One reason was its appearance. The galaxy looked unusually blue. Now, colour might not seem particularly important. After all, many astronomical images are enhanced, processed, and colourised for scientific analysis or public presentation. But colour carries information. A tremendous amount of information. Stars come in different temperatures. Cooler stars tend to appear redder. Hotter stars tend to appear bluer. This relationship gives astronomers a useful tool. By measuring the light coming from a galaxy, they can estimate the types of stars living inside it. A galaxy dominated by blue light often contains large numbers of young hot stars. These stars burn brightly but live relatively short lives. They're cosmic sprinters rather than marathon runners. Massive blue stars consume their fuel rapidly. Many survive only a few million years before ending their lives dramatically. Compared to the age of the universe, a few million years is almost nothing. So when astronomers see a galaxy glowing with blue light, they immediately know that star formation has been occurring recently. I Zwicky 18 appeared extremely active in that regard. Young stars seemed to be everywhere. That alone wasn't enough to cause confusion. Many galaxies form stars. Our own Milky Way continues producing new stars today. The real puzzle emerged when astronomers examined the galaxy's chemical composition. To understand why this mattered, imagine trying to determine the age of a city. You might look at its architecture. You might examine layers beneath the streets. You might search for evidence of earlier generations. Galaxies leave similar clues, not through buildings, but through chemistry. The earliest universe consisted almost entirely of hydrogen and helium. Those two elements dominated cosmic history immediately after the Big Bang. Everything heavier came later. Stars acted as cosmic factories. Inside their cores, nuclear fusion gradually produced heavier elements: carbon, oxygen, nitrogen, silicon, iron, and many others. When stars died, They released those materials into surrounding space. Future generations of stars formed from that enriched gas. The cycle repeated countless times. Over billions of years, galaxies accumulated larger amounts of heavy elements. Astronomers often describe these elements collectively as metals. The terminology can sound strange. To an astronomer, oxygen is a metal. Carbon is a metal, even though your local hardware store would probably disagree. When researchers measured the metallicity of I Zwicky 18, they found something astonishing. The galaxy contained remarkably few heavy elements, far fewer than expected. Its chemical composition appeared primitive, almost untouched, almost youthful. The galaxy seemed chemically closer to conditions found in the early universe than to conditions expected in nearby galaxies. That observation immediately raised eyebrows. Low metallicity suggested that relatively few generations of stars had lived and died there. But how could that be? The universe was already billions of years old. Galaxies were supposed to have extensive histories. Even small dwarf galaxies generally showed evidence of long periods of stellar evolution. Yet, I Zwicky 18 seemed different. Researchers began asking uncomfortable questions. Had they discovered a galaxy that formed unusually late? Had it somehow avoided star formation for billions of years? Could an apparently young galaxy really exist in the modern universe? The implications were enormous. If true, the discovery would challenge assumptions about galaxy formation. Scientists generally believed that galaxies formed early in cosmic history. The details varied. The processes were complex. But the overall picture seemed fairly secure. Galaxies emerged not long after the universe became capable of producing stars. Finding a genuinely young galaxy nearby would force astronomers to rethink important parts of that story. Naturally, not everyone was convinced. Astronomers tend to be cautious, sometimes frustratingly cautious. A researcher may spend years questioning a conclusion before accepting it. This skepticism serves an important purpose. Nature has a habit of fooling people. The universe often looks simpler than it really is. Many discoveries that seem revolutionary at first eventually turn out to have more ordinary explanations. So while some astronomers became excited about the possibility of a truly young galaxy, others urged restraint. Perhaps the galaxy only looked young. Perhaps older stars existed but remained difficult to detect. Perhaps the measurements were incomplete. Perhaps some important piece of the puzzle was missing. The debate intensified. Every new observation seemed to generate additional questions. One challenge involved the galaxy's distance. I Zwicky 18 lies approximately 59 million light-years away. Although that sounds unimaginably far, astronomers considered it relatively nearby. Close enough for detailed study. Far enough to create observational difficulties. At that distance, resolving individual stars becomes challenging. Imagine standing miles away from a city at night. You might see bright clusters of lights. You might identify major features. But distinguishing individual windows would be difficult. Astronomers faced a similar problem. The brightest stars stood out clearly. Fainter stars blended together. And unfortunately, the stars they most wanted to find were precisely the faint ones. Old stars, ancient stars, the stellar equivalent of senior citizens quietly sitting in the background. Those stars hold crucial information about a galaxy's history. If an old stellar population existed inside I Zwicky 18, then the galaxy wasn't truly young. It would merely be experiencing a recent burst of star formation. That scenario would be much less revolutionary. Still interesting, still important. But not extraordinary. The search became increasingly intense. Throughout the 1980s and 1990s, improved instruments provided better measurements. Astronomers studied the galaxy's gas clouds, analysed its light, compared observations with theoretical models. The evidence remained intriguing. Again and again, I Zwicky 18 appeared unusually primitive. The galaxy almost seemed determined to maintain its mystery. One reason the object fascinated researchers was because it offered a possible glimpse into the distant past. Observing the early universe directly is difficult. Extremely distant galaxies appear faint. Their light has travelled for billions of years. Details become challenging to measure. But if I Zwicky 18 truly resembled a young galaxy, astronomers might have a nearby laboratory for studying conditions similar to those present shortly after the Big Bang. That possibility was incredibly valuable. Imagine trying to understand ancient human history. You could travel across the world searching for fragile archaeological remains, or you might discover an exceptionally well-preserved site nearby. Naturally, you'd want to investigate. I Zwicky 18 promised something similar, a chance to examine youthful galactic conditions without looking billions of light years away. The excitement spread. Papers appeared, conferences featured discussions, arguments developed. Researchers proposed competing interpretations. Some believed the galaxy represented a genuinely young system. Others argued that hidden older stars almost certainly existed. The disagreement wasn't simply academic. It touched fundamental questions about cosmic evolution. How do galaxies form? How quickly do they evolve? Can star formation remain dormant for billions of years? Can a galaxy effectively postpone its development? Nobody knew for certain. Adding to the puzzle was the galaxy's irregular structure. Unlike grand spiral galaxies with clearly defined shapes, I Zwicky 18 appears somewhat chaotic. Bright regions of star formation dominate its appearance. Gas clouds twist through the system. The overall structure lacks the orderly elegance often associated with famous galaxies. That irregularity made interpretation harder. Astronomers couldn't simply apply standard assumptions. The galaxy seemed determined to resist easy classification. Meanwhile, observations revealed ongoing bursts of star formation. New stars continued emerging from enormous clouds of gas. Some of these stars were extraordinarily massive. Massive stars shine intensely. They produce enormous amounts of ultraviolet radiation. They influence surrounding gas. They shape the appearance of entire regions. The galaxy almost seemed alive with youthful energy. Everywhere researchers looked, evidence pointed toward recent stellar activity. Yet recent activity doesn't necessarily mean recent origin. That distinction became increasingly important. A city experiencing a construction boom isn't necessarily a newly founded city. Likewise, a galaxy forming stars rapidly isn't necessarily a newly born galaxy. The challenge was separating current events from ancient history. Researchers needed deeper observations, sharper images, more sensitive instruments. They needed a way to peer through the galaxy's bright young stars and search for older populations hidden underneath. At the time, accomplishing that task remained difficult. The available technology simply wasn't powerful enough. Astronomers could suspect, they could estimate, they could argue, but they couldn't yet settle the question conclusively. That uncertainty made I Zwicky 18 one of the most intriguing dwarf galaxies ever studied. Every new observation seemed to support two conflicting ideas simultaneously. The galaxy looked incredibly young. The universe insisted it should be old. Both statements appeared reasonable. Both couldn't be entirely correct. Somewhere between those two possibilities lay the truth. As the years passed, anticipation grew around a particular instrument, a telescope capable of seeing farther and more clearly than any optical observatory before it. A telescope orbiting above Earth's atmosphere. A telescope that would eventually provide the evidence astronomers desperately needed. Because if hidden ancient stars existed within I Zwicky 18, this instrument had a chance of finding them. And if no such stars appeared, then the case for an extraordinarily young galaxy would become much stronger. The mystery had reached a point where better theories were no longer enough. Astronomers needed better eyes. Before astronomers could decide whether I Zwicky 18 was genuinely young or merely pretending to be young, they faced a more fundamental challenge. They needed to understand what they were actually looking at. That may sound like an odd statement. After all, a telescope points at a galaxy, gathers light and produces an image. Simple enough, except it isn't. The moment we begin observing distant objects in space, something remarkable happens. We stop looking across distance and start looking across time. Every observation becomes a journey into history. Every galaxy becomes a record of the past. Every photon arriving at a telescope acts like a tiny messenger carrying information from another era. This is one of the strangest facts in astronomy. Unlike most sciences, astronomers cannot interact directly with their subjects. A geologist can pick up a rock. A biologist can study a living organism. A chemist can perform an experiment repeatedly. Astronomers don't enjoy those luxuries. No one can visit a distant galaxy, collect samples and return home before dinner. Everything astronomers know comes from light. That's it. Light is their witness, their evidence, their storyteller. Fortunately, light turns out to be an extraordinarily good storyteller. The reason begins with the simple fact that many people learn in school but rarely stop to appreciate. Light travels at a finite speed, fast certainly, very fast, about 300,000 kilometers every second, fast enough to circle Earth more than 7 times in a single second, fast enough to travel from Earth to the Moon in roughly 1.3 seconds, fast enough to make everyday life seem instantaneous. Yet despite that incredible speed, light still requires time to travel. And because it requires time, every observation contains a delay. When you look at the moon, you're not seeing the moon as it is right now. You're seeing the moon as it was about 1.3 seconds ago. The difference is tiny. Nobody loses sleep over a 1-second delay from the moon. The situation changes dramatically when distances become larger. The sun sits approximately 150 million kilometers away. Sunlight requires around 8 minutes to reach Earth. If the sun somehow vanished, which fortunately it won't, we wouldn't know immediately. For 8 minutes everything would appear perfectly normal. The sunlight already on its way would continue arriving. Only afterward would the absence become visible, so even our nearest star is observed in the past. Astronomy quietly operates inside a time machine. The farther away something is, the further back in time we see. Consider a star located 100 light-years from Earth. The light reaching us tonight left that star 100 years ago. While you're listening to this story, photons that began their journey before the First World War may be arriving at telescopes. The star itself might look completely different today. Astronomers wouldn't know yet. The information is still travelling. Increase the distance further. 1,000 light-years, 10,000, 1 million. The past grows deeper and deeper. Eventually distance becomes history. This realization transformed astronomy. Researchers understood that the universe itself preserves a record of its own development. Looking farther away means looking farther back. The cosmos provides snapshots from different eras. Nearby objects reveal relatively recent history. Extremely distant objects reveal ancient history. In a sense, the observable universe resembles a vast museum. Each distance corresponds to a different exhibit. Each galaxy occupies a different point in cosmic time. And because light moves at a fixed speed, those exhibits remain arranged exactly where nature placed them. When astronomers observe a galaxy 1 billion light-years away, they see it as it existed 1 billion years ago. When they observe a galaxy 10 billion light-years away, they witness conditions from 10 billion years in the past. This creates an extraordinary opportunity. Scientists can study cosmic evolution directly, not perfectly, not completely, but far more effectively than many people realize. Imagine a historian somehow obtaining photographs from every century of human civilization. The development of cities, cultures, and technologies would become easier to understand. Astronomers enjoy something similar. The universe provides images from different periods of its own history. Those images allow researchers to reconstruct the story of cosmic evolution. Naturally, the process isn't straightforward. The farther away an object becomes, the fainter it appears. distance dims light. A galaxy visible nearby may become extremely difficult to detect when viewed across billions of light years. This challenge occupied astronomers for generations. Larger telescopes helped, better detectors helped, space-based observatories helped. Each technological improvement allowed researchers to push farther into the past. The results were astonishing. As observations improved, astronomers discovered galaxies existing when the universe was only a fraction of its current age. Some appeared less than 1 billion years after the Big Bang. Others emerged even earlier. Each discovery extended humanity's view deeper into cosmic history. The universe gradually revealed its childhood. Yet those distant galaxies presented a problem. They were difficult to study in detail. Imagine standing on a mountaintop and trying to identify individual windows in a city hundreds of kilometers away. You might recognize the city itself. You might estimate its size. But countless details would remain hidden. The sim limitation affects distant galaxies. Astronomers can detect them, measure them, analyze them, but many fine details remain frustratingly difficult to observe. This is where I Zwicky 18 became especially interesting. Remember its distance, approximately 59 million light-years, far enough to place it beyond our immediate cosmic neighbourhood, close enough to study in far greater detail than truly ancient galaxies. That combination made it valuable. If I Zwicky 18 genuinely resembled young galaxies from the early universe, researchers might possess a nearby laboratory for investigating ancient conditions. Instead of peering across 10 or 12 billion years of cosmic history, they could examine something relatively close. The comparison was irresistible. Imagine trying to understand the daily life of ancient civilizations. One approach involves studying distant ruins. Another involves discovering a modern community preserving remarkably similar traditions. Both approaches provide information. The second often allows greater detail. For a time, many astronomers wondered whether I Zwicky 18 might offer something similar for galaxy formation. Perhaps it represented a nearby example of what galaxies looked like long ago. Perhaps studying it could reveal clues about conditions that existed shortly after the universe began building large structures. That possibility motivated intense interest. Yet before anyone could draw conclusions, they needed to understand how galaxies evolve over time. The universe does not remain static. Galaxies change continuously. Stars form. Stars die. Gas clouds collapse. Collisions occur. Chemical compositions shift. Every process leaves traces. Every generation modifies the next. As a result, galaxies carry historical records inside themselves. Astronomers often describe this concept using the term stellar populations. Different generations of stars coexist within many galaxies. Young stars occupy one age group. Older stars belong to another. Ancient stars belong to yet another. Each population tells part of the story. Finding those populations is like examining layers in an archaeological site. The deepest layers often contain the oldest evidence. The upper layers reveal more recent events. Galaxies work similarly. Ancient stars preserve information from early periods. Young stars reveal current activity. By studying both, researchers reconstruct the timeline. This approach becomes especially important when direct observation of the past proves impossible. No telescope can watch a galaxy evolve for billions of years. Human lifetimes are far too short. Instead, astronomers infer history from evidence visible today. A galaxy effectively serves as its own historical archive. I Zwicky 18 complicated this process because the archive appeared strangely incomplete. The galaxy contained abundant evidence of recent star formation. Young stars dominated observations. Bright blue regions attracted attention immediately. Yet signs of ancient stellar populations remained elusive. The expected historical layers seemed missing. That absence generated enormous curiosity. Imagine opening a history book and discovering that the first several chapters had vanished. You would immediately want to know why. Were they removed? Were they never written? Had you opened the wrong book? Astronomers asked comparable questions about I Zwicky 18. The galaxy appeared to possess a vivid present but an uncertain past. That uncertainty became one of the central mysteries. Adding further complexity was the expanding universe itself. Early in the 20th century, astronomers discovered that galaxies generally move away from one another. Space itself expands. Distances increase over time. This expansion stretches light travelling through the cosmos. The effect is known as redshift. Light emitted at shorter wavelengths gradually shifts toward longer wavelengths during its journey. The farther a galaxy lies from Earth, the greater the effect tends to be. Redshift provides another way to measure cosmic history. By studying it, astronomers estimate distances and reconstruct the universe's expansion. The technique transformed cosmology. Suddenly, researchers possessed a tool for mapping the large-scale structure of the universe. They could estimate how far away galaxies were. They could calculate how long light had travelled. They could determine which cosmic era they were observing. Every distant galaxy effectively arrived with a timestamp. I Zwicky 18 fit into this broader picture in an intriguing way. Unlike galaxies observed near the edge of the observable universe, it wasn't ancient light from the dawn of cosmic history. Its light began travelling roughly 59 million years ago. At that time, dinosaurs were long extinct. Mammals dominated Earth, yet humanity did not exist. The first humans would not appear for tens of millions of years. The galaxy we observe today therefore represents a version of I Zwicky 18 that predates every human being who has ever lived. That's worth pausing to consider. Every image, every measurement, every observation, all of it describes a galaxy as it existed before our species emerged. The present-day version remains invisible for now. Its latest chapter continues travelling toward us through space. Astronomy constantly reminds us that the universe operates on scales difficult to grasp. Distances become times. Times become histories. Histories become observations. A telescope pointed toward the sky effectively functions as a historical instrument. It records messages sent long ago. Some messages began their journey before civilization, some before humanity, some before Earth itself existed. And that extraordinary fact helps explain why I Zwicky 18 attracted such attention. Astronomers weren't merely studying a small dwarf galaxy. They were attempting to understand where that galaxy belonged within the larger timeline of cosmic evolution. Was it genuinely youthful? Was it merely preserving youthful characteristics? Did it represent a relic of conditions common billions of years ago? Or was it something entirely different? Answering those questions required more than measuring distance. Researchers needed reliable ways to determine age, not the age of individual stars alone. The age of an entire galaxy, a far more difficult challenge, because galaxies don't arrive with birth certificates. They don't announce when they formed. Instead, astronomers must gather clues: light, chemistry, stellar populations, gas clouds. Every piece contributes to the investigation. By the time astronomers began debating the age of I Zwicky 18, they weren't starting from scratch. They already had decades of observations, decades of theories, decades of evidence describing how galaxies form and evolve. That background is important because it explains why so many researchers initially reacted with skepticism when the possibility of a genuinely young galaxy appeared. The idea wasn't impossible. Science rarely deals in impossibilities. The problem was that it seemed unlikely, very unlikely. To understand why, we need to step back and look at the broader history of the universe itself. Galaxies don't appear randomly. They are products of cosmic evolution. Their existence is tied to events that began almost 14 billion years ago. The story starts with the Big Bang, not an explosion in space, not a fireball expanding into emptiness. Instead, it was the rapid expansion of space itself. The universe began in an extremely hot, extremely dense state. As expansion continued, temperatures gradually fell. The early universe was remarkably simple. There were no galaxies, no stars, no planets, no black holes, no astronomers arguing about dwarf galaxies. For a long time, there wasn't much to see at all. Matter existed. Energy existed. But the complex structures we recognize today had not yet formed. During the first few minutes, hydrogen and helium began emerging. Those two elements became the universe's primary ingredients. In fact, they still dominate today. Nearly every star you can see owes its existence to those early events. For hundreds of thousands of years, however, conditions remained too hot for atoms to form properly. Light couldn't travel freely. The universe resembled a dense fog. Photons bounced constantly from particle to particle. Nothing could see anything. Not that there was anyone around to try. Eventually, temperatures dropped enough for electrons and atomic nuclei to combine. Atoms formed. The cosmic fog cleared. Light suddenly travelled vast distances. Astronomers still observe the ancient light today as the cosmic microwave background. It acts almost like a baby photograph of the universe. Not a perfect photograph, not a detailed one, but a remarkably useful snapshot of conditions shortly after the beginning. One of the most important discoveries hidden inside that ancient light involves tiny fluctuations. The universe wasn't perfectly uniform. Some regions contained slightly more matter than others. The differences were incredibly small, almost unimaginably small. Yet gravity has a remarkable talent. It doesn't require large differences. Given enough time, even tiny advantages become significant. Regions containing slightly more matter exerted slightly stronger gravitational pull. They attracted additional material. That additional material increased their gravity, which attracted even more material. The process repeated for millions and eventually billions of years. Gravity became the universe's great organizer. Gradually, enormous clouds of gas gathered. The first stars ignited. Small structures merged into larger ones. Galaxies began taking shape. This process happened early, very early. Observations from modern telescopes show that galaxies already existed when the universe was only a few 100 million years old. That may sound like a long time. On human scales, it certainly is. On cosmic scales, it represents infancy. Imagine compressing the universe's entire history into a single year. Galaxies appeared during the first days of January. Human civilization would not arrive until the final seconds before midnight on December 31st. That's how early galaxy formation occurred. Researchers have spent decades studying this process. The details remain complicated. Individual galaxies follow different paths. Some grow rapidly, some evolve slowly, some merge repeatedly, some remain relatively isolated. Yet the overall picture remains remarkably consistent. Galaxies began forming near the beginning of cosmic history. This expectation became one of the foundations of modern cosmology. Observation supported it. Computer simulation supported it. Theoretical models supported it. Everything pointed toward the same conclusion. The universe started building galaxies long ago, very long ago. Consequently, astronomers expected galaxies observed today to be ancient. Not necessarily ancient-looking, not necessarily inactive, but ancient in origin. Even galaxies currently producing new stars should possess old foundations underneath. The stellar equivalent of deep roots. Think about a city. A city may construct new buildings every year. It may add roads, expand neighborhoods, replace old structures. Yet beneath those changes lies a longer history. The city itself remains older than its newest buildings. Galaxies operate similarly. New stars can form continuously. Entire regions may appear youthful and energetic, but the galaxy's overall existence stretches much further into the past. This expectation seemed especially reasonable because star formation is generally difficult to stop completely. Gas clouds collapse under gravity. Stars emerge. Those stars influence their surroundings. New generations follow. The cycle tends to continue whenever sufficient gas remains available. A galaxy would need unusual circumstances to avoid star formation for billions of years. That possibility wasn't impossible, it simply wasn't expected. As evidence accumulated throughout the 20th century, astronomers identified old stars almost everywhere they looked. Large galaxies contained ancient stellar populations. Small galaxies contained ancient stellar populations. Even systems experiencing vigorous current star formation generally revealed evidence of much older stars lurking in the background. Again and again, observations reinforced the same basic idea. Galaxies possess long memories. They preserve traces of their past. Those traces may become difficult to detect. They may hide beneath younger populations, but they usually exist. This pattern became so familiar that many researchers considered it almost obvious. Of course, galaxies are old. What else would they be? Then I Zwicky 18 arrived. Or more accurately, observations of I Zwicky 18 began suggesting something unusual. The galaxy appeared to violate expectations. Not completely, not definitively, but enough to generate concern. Its low metallicity immediately stood out. Remember what metallicity represents. Heavy elements produced by generations of stars. Each generation enriches surrounding gas. Future stars inherit those materials. The process gradually increases chemical complexity. Over billions of years, metallicity tends to rise. Not always smoothly, not always uniformly, but generally. That trend makes low metallicity noteworthy. It suggests limited chemical evolution. Limited chemical evolution suggests relatively few generations of stars, and relatively few generations of stars can suggest youth. Astronomers understood this logic perfectly. The problem was that the conclusion conflicted with broader expectations. Suppose someone told you they had discovered a tree only a few months old growing in the middle of an ancient forest. You might believe them, but you'd probably ask questions. Lots of questions. You'd want evidence. You'd wonder whether the tree merely looked young. You'd examine the surrounding environment. You'd investigate before accepting the claim. Researchers approached I Zwicky 18 similarly. The galaxy appeared youthful, yet galaxies were supposed to be ancient. Both statements demanded explanation. Some astronomers suspected observational limitations. Perhaps older stars existed but remained hidden. Bright young stars can dominate a galaxy's appearance. Massive blue stars produce enormous amounts of light. They attract attention immediately. Ancient stars, by comparison, tend to appear fainter. Detecting them requires sensitive instruments. The situation resembles visiting a city at night during a fireworks display. The fireworks command your attention. They dominate the sky. Meanwhile, countless ordinary lights remain present but easy to overlook. Young stars can create similar observational challenges. Researchers therefore wondered whether I Zwicky 18's apparent youthfulness resulted partly from visibility. Maybe older populations lurked underneath the bright regions of recent star formation. Finding them would simply require better observations. Others considered more exotic possibilities. Could galaxy formation occur unusually late under certain circumstances? Could some dwarf galaxies spend billions of years accumulating gas before finally igniting major star formation? Could environmental factors delay development? Theoretical discussions expanded rapidly. One reason these debates mattered so much is because galaxies occupy a central role in cosmic evolution. Galaxies are not minor details within the universe. They are among its primary structures. Stars form inside galaxies. Planetary systems form around stars. Life, as far as we know, emerges within planetary systems. Understanding galaxies means understanding the environments where nearly everything else happens. If a fundamental assumption about galaxy ages proved incorrect, researchers would need to revisit many related ideas. Science occasionally experiences such moments. Most discoveries fit comfortably within his existing frameworks. Some force adjustments, a few demand substantial revision. Nobody knew which category I Zwicky 18 would eventually occupy. That uncertainty attracted attention from around the astronomical community. Meanwhile, observations of distant galaxies continued improving. New instruments revealed increasingly ancient systems. Researchers identified galaxies existing when the universe was remarkably young. Ironically, some of those distant galaxies appeared surprisingly mature. Massive stars had already formed. Chemical enrichment had already begun. Complex structures already existed. The early universe seemed capable of producing galaxies quickly. That evidence strengthened the expectation that nearby galaxies should possess long histories. If galaxies formed rapidly near the beginning of cosmic time, why would one remain genuinely young today? The question became harder to ignore. Another factor involved dark matter. Although invisible, dark matter appears to play a crucial role in galaxy formation. Massive halos of dark matter provide gravitational frameworks around which ordinary matter accumulates. Computer simulations suggest these structures emerged early. Gas flowed into them, stars formed, galaxies grew. Again, the overall picture pointed toward ancient origins. Even small galaxies likely began assembling billions of years ago. Everything seemed to reinforce the same conclusion, which made I Zwicky 18 increasingly fascinating. The galaxy wasn't simply unusual. It challenged expectations developed from multiple independent lines of evidence. Whenever that happens in science, researchers pay attention. Sometimes the anomaly disappears after better observations. Sometimes it reveals flaws in existing assumptions. Either outcome proves valuable, one improves measurements, the other improves understanding. For years, astronomers found themselves caught between those possibilities. The galaxy remained stubbornly mysterious. Evidence suggested youth. Theory suggested age. Observations offered clues but not certainty. The debate continued. And perhaps the most interesting aspect of the entire situation was that nobody actually wanted a particular answer. Scientists often receive unfair portrayals in popular culture. People sometimes imagine researchers defending cherished beliefs at all costs. Real science usually works differently. Astronomers would have been delighted by either outcome. A genuinely young galaxy would be extraordinary. A galaxy that only appeared young would also teach important lessons. Both possibilities offered opportunities for discovery. The challenge was determining which explanation nature had chosen. That task required moving beyond broad expectations. Researchers needed specific methods for measuring galactic age, not guesses, not assumptions, actual evidence. They needed ways to investigate stellar populations directly, ways to identify ancient stars if they existed, ways to determine whether the galaxy possessed hidden historical layers beneath its youthful appearance. Fortunately, astronomy had developed several powerful techniques for doing exactly that. For a while, the debate surrounding I Zwicky 18 revolved around chemistry. The galaxy contained remarkably small amounts of heavy elements. Its gas appeared primitive. Its bright blue stars suggested vigorous recent star formation. Those observations were intriguing, but they weren't enough to settle the question. Astronomers needed stronger evidence, much stronger, because chemistry can sometimes be misleading. Galaxies are complicated places. Gas can flow in, gas can flow out. Star formation can occur in bursts separated by long quiet periods. A low metallicity does not automatically prove that a galaxy is young. It merely raises the possibility. The real test involves something else entirely. Stars, specifically old stars, ancient stars. The stellar elders that should have been present if I Zwicky 18 truly possessed a long history. And that is where the mystery became especially frustrating. Astronomers kept looking for those stars, they couldn't find them, at least not at first. To understand why this was so important, imagine walking into a city that supposedly dates back thousands of years. You would expect to find evidence of that history everywhere. Old foundations, ancient roads, historic buildings, artifacts buried beneath newer construction. Even if modern skyscrapers dominated the skyline, traces of earlier generations should still remain. Now imagine searching carefully and finding almost nothing. The absence itself would become a clue. You would immediately start asking questions. Was the city actually younger than expected? Had earlier structures somehow vanished? Were you simply looking in the wrong places? Astronomers faced a similar situation with I Zwicky 18. The galaxy seemed full of young stars, bright, hot blue stars, stars that had formed relatively recently. But where were the ancient populations that should have accumulated over billions of years? Where were the stellar grandparents, the stellar great-grandparents, the stars old enough to remember the galaxy's earliest chapters? Their apparent absence created one of the most fascinating mysteries in modern astronomy. Part of the challenge came from the fact that stars age in predictable ways. Unlike people, stars don't become wiser with age, but they do become easier to classify. Astronomers understand stellar evolution remarkably well. They know how stars are born. They know how stars change over time. They know how mass influences a star's lifespan. And most importantly, they know what old stars should look like. Young stars tend to be bright. Massive young stars are especially bright. Some can shine hundreds of thousands or even millions of times more intensely than our sun. They dominate images. They attract immediate attention. Old stars are different. Many are smaller, cooler, dimmer. They don't announce themselves dramatically. Instead, they form a quiet background population. Finding them often requires patience and powerful instruments. This creates an observational challenge. Imagine standing on a hill overlooking a city during a fireworks display. The explosions dominate the scene. Your eyes naturally focus on the brightest lights. Meanwhile, thousands of ordinary street lamps continue glowing beneath the spectacle. They're still there. They're simply harder to notice. Young star-forming regions create a similar effect. The brilliance of youthful stars can overwhelm the faint light coming from older populations. Astronomers understood this possibility from the beginning. The missing ancient stars might not actually be missing. They might simply be hidden. That explanation seemed reasonable, yet years passed without clear evidence. Observations continued. Debates intensified. Researchers studied every available image. Some argued that ancient stars must exist. Others wondered whether the galaxy genuinely lacked them. The possibility remained controversial. At the heart of the discussion lay a fundamental question. How do you determine whether a galaxy contains old stars? The answer involves one of astronomy's most powerful tools, a diagram known as the Hertzsprung-Russell diagram. The name isn't particularly catchy. Astronomers are excellent at discovering things and somewhat less talented at marketing. Nevertheless, this diagram transformed stellar astronomy. It organizes stars according to brightness and temperature. Different types of stars occupy different regions. As stars age, they move through predictable stages. Their positions change, their properties change, their appearance changes. By examining large populations of stars, astronomers can reconstruct a galaxy's history. The process resembles studying the age distribution of people in a town. Suppose you visit a community and discover only children and young adults. That would seem unusual. Most populations contain individuals of many ages. The same principle applies to galaxies. A mature galaxy should contain stars representing multiple generations. Young stars, middle-aged stars, ancient stars. The distribution reveals the story. Zwicky 18 appeared oddly skewed. Again and again, observations highlighted youthful populations. The older generations remained elusive. This situation became increasingly significant because other dwarf galaxies generally revealed ancient stars without much difficulty. Researchers had examined numerous small galaxies throughout the nearby universe. Most showed evidence of stellar populations billions of years old. Even galaxies with low metallicity typically contained ancient stars. That pattern reinforced the expectation that I Zwicky 18 should possess them as well. Yet confirmation remained frustratingly out of reach. Some astronomers began proposing more exotic possibilities. Perhaps the galaxy had formed unusually late. Perhaps it had remained dormant for most of cosmic history. Perhaps some rare combination of circumstances delayed significant star formation until relatively recently. These ideas generated excitement because they challenged conventional wisdom. If correct, they would force researchers to rethink important aspects of galaxy evolution. Not completely. The overall framework of cosmology would remain intact, but certain assumptions might require revision. The possibility was enticing. Science advances through puzzles, and I Zwicky 18 had become a particularly stubborn puzzle. Meanwhile, telescope technology continued improving. Throughout the 20th century, astronomy experienced a steady revolution in observational capability. Each generation of instruments surpassed the previous one. Researchers observed fainter objects, resolved finer details, measured weaker signals. Questions that once seemed impossible gradually became approachable. The search for ancient stars benefited enormously from these improvements. Yet even with better instruments, the challenge remained difficult. Distance played a major role. Remember that I Zwicky 18 lies approximately 59 million light-years away, close enough to study, far enough to complicate everything. At such distances, individual stars become difficult to distinguish. Bright stars stand out, faint stars blend together, and unfortunately, many ancient stars belong to precisely the faint category astronomers were trying to investigate. The galaxy seemed almost designed to test observational limits. Researchers needed exceptional precision. They needed exceptionally sharp images. Most importantly, they needed a telescope capable of seeing through the confusion created by younger stellar populations. As the debate continued, attention increasingly shifted toward a particular class of stars known as red giants. These stars occupy a crucial stage of stellar evolution. Many older stars eventually expand and cool, becoming red giants. Although not necessarily the oldest stars in existence, red giants often serve as useful indicators of ancient populations. Finding them would provide powerful evidence that the galaxy contained stars billions of years old. The search became almost detective-like. Astronomers weren't looking for a single ancient star. They were looking for a pattern, a population, a statistical signature revealing a hidden history. Imagine entering a library after a fire. Most books have vanished, only fragments remain. Yet, by examining those fragments carefully, historians might reconstruct the library's contents. Astronomers approached Zwicky 18 in much the same way. Every faint point of light mattered. Every observation contributed another clue. The mystery became increasingly famous because it touched a broader question. How reliable are appearances in astronomy? Galaxies often look younger or older than they really are. A recent burst of star formation can dramatically alter a galaxy's appearance. For a brief period, bright blue stars dominate observations. The galaxy seems youthful, energetic, fresh. Yet beneath that temporary display may lie billions of years of hidden history. Human beings do something similar. A city may build new neighborhoods, install modern infrastructure, construct gleaming skyscrapers. Visitors might describe it as young. Yet underneath those modern layers, ancient foundations may still exist. Galaxies can be equally deceptive. The challenge lies in distinguishing appearance from reality. By the late 20th century, astronomers found themselves trapped between two possibilities. Either I Zwicky 18 truly lacked ancient stars, or the ancient stars remained just beyond observational reach. Neither explanation could yet be proven. Both remained plausible. The tension persisted. Research papers continued appearing. Some argued strongly for youth, others argued for hidden age. The scientific conversation grew increasingly detailed. One team would publish evidence supporting one interpretation. Another team would point out limitations. Additional observations would follow. Gradually, the debate narrowed. Researchers began agreeing on one thing: better data was essential. The existing observations simply weren't sufficient. The galaxy sat frustratingly close to certainty, close enough to inspire confidence, not close enough to settle the issue. That situation can be surprisingly uncomfortable for scientists. Uncertainty is expected. Complete ignorance is manageable. Partial knowledge often proves more difficult. You know enough to recognize the mystery but not enough to solve it. I Zwicky 18 occupied exactly that territory. Then came a major development. A telescope orbiting high above Earth's atmosphere. A telescope capable of extraordinary resolution. A telescope that had already transformed numerous areas of astronomy. The Hubble Space Telescope. Hubble offered something previous observations lacked: clarity. Atmospheric turbulence blurs images obtained from the ground. Even the best Earth-based observatories must contend with air constantly moving above them. Hubble avoided that problem entirely. Operating in space, it could observe with remarkable sharpness. Suddenly, objects once hidden became visible. Structures once blurred became distinct. Faint stars once lost in confusion emerged from the background. Astronomers immediately recognized what this meant for Zwicky 18. If ancient stars existed, Hubble might finally reveal them. Years of debate had led to this moment. The mystery of the missing ancient stars was no longer purely theoretical. Researchers now possessed a realistic opportunity to search directly. The stakes were enormous. A confirmed population of old stars would dramatically alter interpretations of the galaxy. The evidence for extreme youth would weaken. The galaxy would remain fascinating, but for different reasons. On the other hand, continued failure to find old stars would strengthen the argument that I Zwicky 18 represented something genuinely extraordinary. The observations became some of the most anticipated in dwarf galaxy research. Astronomers prepared to examine the galaxy more carefully than ever before, not merely its gas, not merely its chemistry, not merely its brightest regions. They wanted to probe its history, its deepest layers, its oldest memories. By the late 20th century, the discussion surrounding I Zwicky 18 had evolved into something much larger than the study of a single dwarf galaxy. Researchers were no longer asking whether the galaxy was unusual. That much seemed obvious. The real question had become far more provocative. Could we actually be looking at a genuinely young galaxy? It was the kind of question that immediately captures attention because it appears to challenge common sense. Not everyday common sense, cosmic common sense. The understanding astronomers had built over decades of observation. After all, galaxies were supposed to be old. That expectation wasn't based on tradition or habit. It emerged from evidence. The universe began forming galaxies billions of years ago. Large galaxies appeared early. Small galaxies appeared early. Everywhere astronomers looked, they found signs of ancient stellar populations. Yet I Zwicky 18 seemed reluctant to cooperate. Again and again, it displayed characteristics associated with youth. Its chemical composition appeared primitive. Its bright blue stars suggested recent activity. And despite repeated searches, evidence for substantial ancient stellar populations remained frustratingly difficult to confirm. Naturally, some astronomers began entertaining possibilities that previously seemed unlikely. Maybe the galaxy really was young. Not young compared to a human being, not young compared to Earth. Young compared to other galaxies. The distinction mattered enormously. Even a galaxy only a few 100 million years old would qualify as remarkably youthful in a universe approaching 14 billion years of age. To appreciate how extraordinary that would be, imagine discovering a newborn tree growing in the middle of a forest that had existed for thousands of years. The tree itself wouldn't be unusual. Trees are born all the time. The mystery would involve timing. Why now? Why there? Why so much later than everything around it? Astronomers found themselves asking similar questions about I Zwicky 18. If the galaxy truly formed recently, what prevented it from forming earlier? Why would galaxy formation occur billions of years after most galaxies had already begun evolving? What conditions could delay the process for so long? The questions multiplied faster than the answers. One proposal suggested that the galaxy might have spent most of cosmic history as a diffuse cloud of gas. Perhaps gravity had been insufficient to trigger substantial star formation. Perhaps internal conditions remained stable for billions of years. Then, for some reason, the balance changed. Gas began collapsing. Stars began forming. The galaxy effectively awakened after an extraordinarily long delay. It was an intriguing idea. Unfortunately, intriguing ideas are not the same as evidence. Astronomers needed more than speculation. They needed mechanisms. They needed calculations. Most importantly, they needed observations capable of supporting such a dramatic claim. The challenge was that galaxies generally don't behave this way. Gravity is patient. Given enough time, it usually gets what it wants. Gas clouds attract additional gas. Density increases. Collapse begins. Stars emerge. The process may proceed slowly. It may proceed unevenly. But stopping it completely for billions of years seemed difficult. Researchers therefore examined alternative explanations. Perhaps I Zwicky 18 wasn't actually young. Perhaps it merely resembled galaxies from the early universe. That possibility became increasingly attractive because appearances can be deceptive in astronomy. A galaxy experiencing an intense burst of star formation can temporarily look much younger than it really is. The newest stars dominate the light. Their brightness overwhelms older populations. Observers see the youthful surface while ancient layers remain hidden underneath. Human history provides an interesting comparison. Imagine visiting a city that recently experienced a construction boom. New buildings dominate the skyline. Fresh roads appear everywhere. Modern architecture attracts attention. A visitor might describe the city as young. Yet beneath those visible changes may lie centuries of history. The city itself remains old even if parts of it look new. Galaxies can create similar illusions. Recent activity often disguises ancient origins. This explanation satisfied many astronomers because it aligned comfortably with existing theories. The galaxy could remain unusual without requiring major revisions to cosmology. Still, the observations refused to make things easy. Low metallicity remained a significant problem. Most old galaxies accumulate heavier elements over time. Every generation of stars enriches surrounding gas. The process gradually transforms chemical composition. Yet I Zwicky 18 contained remarkably small amounts of those heavier elements. Its chemistry genuinely resembled what astronomers expected from much younger systems. This forced researchers into an uncomfortable position. Neither explanation seemed perfect. A truly young galaxy challenged expectations about galaxy formation. An ancient galaxy with extremely primitive chemistry required its own explanation. Nature rarely provides simple choices. Instead, it offers complicated situations where every answer raises new questions. I Zwicky 18 excelled at creating exactly that kind of situation. As observations improved, astronomers began comparing the galaxy to systems observed in the distant universe. This comparison proved especially fascinating. Remember that looking across great distances means looking back in time. Many distant galaxies reveal conditions that existed billions of years ago. Some of those galaxies share characteristics with I Zwicky 18, low metallicity. Active star formation, primitive chemical environments. The similarities were striking. Researchers started wondering whether I Zwicky 18 might function as a nearby analogue for ancient galaxies, not because it actually formed recently, because it preserved conditions resembling those found much earlier in cosmic history. That distinction became increasingly important. A galaxy can behave like a young galaxy without literally being young. The difference sounds subtle. Scientifically, it is enormous. Suppose archaeologists discovered an isolated community preserving customs from centuries ago. The people themselves wouldn't be ancient. The community wouldn't have travelled through time, yet certain aspects of their culture might resemble earlier periods of history. Astronomers considered whether something similar could be happening here. Perhaps I Zwicky 18 preserved primitive conditions long after most galaxies had evolved beyond them. That possibility generated considerable interest because it offered a valuable scientific opportunity. Researchers desperately want nearby laboratories for studying ancient processes. The early universe remains difficult to observe directly. Even the most powerful telescopes face limitations. Distant objects appear faint. Details become blurred. Interpretation becomes challenging. A nearby galaxy displaying ancient characteristics would provide an extraordinary resource. Scientists could investigate processes that shaped the early universe without peering billions of light years into space. In many ways, that prospect was almost as exciting as finding a genuinely young galaxy. Meanwhile, computer simulations entered the discussion. Modern cosmology relies heavily on simulations. Researchers use powerful computers to model galaxy formation under various conditions. These simulations incorporate gravity, gas dynamics, dark matter, star formation, and many other physical processes. By comparing simulated galaxies with real observations, astronomers test their understanding of the universe. When researchers attempted to reproduce systems like I Zwicky 18, they discovered something interesting. Galaxies with extremely low metallicities could emerge naturally under certain circumstances, not because they were newly formed, because their evolutionary histories differed from those of more typical galaxies. Perhaps star formation occurred inefficiently. Perhaps gas inflows diluted heavier elements. Perhaps energetic events expelled enriched material into surrounding space. Several mechanisms appeared capable of maintaining primitive chemistry longer than expected. This realization complicated the debate. The evidence for genuine youth became less overwhelming. At the same time, the galaxy remained remarkably unusual. No single explanation solved every puzzle. The mystery persisted. One of the most compelling aspects of the discussion involved timing. Galaxies evolve over billions of years. Human observations span decades. Astronomers therefore see only brief snapshots. Imagine trying to understand a person's entire life after observing them for a few seconds. The task would be difficult. Galaxies present a similar challenge. Researchers infer long histories from limited observations. Most of the time, the evidence points clearly in one direction. I Zwicky 18 refused to cooperate. Every observation seemed to support multiple interpretations. That ambiguity made the galaxy famous, not because it provided answers, because it generated uncertainty. Scientists often learn more from uncertainties than certainties. Certainties can become comfortable. Uncertainties force investigation. For years, astronomers found themselves balanced between two possibilities. Perhaps they had discovered one of the youngest galaxies ever observed, or perhaps they had discovered one of the best impersonators. Both outcomes would be important. Both would teach valuable lessons. The challenge lay in determining which was correct. As more observations accumulated, attention increasingly focused on the search for ancient stars. Everything seemed to return to that issue. If a substantial population of old stars existed, the galaxy could not be genuinely young. The debate would shift toward understanding why it looked youthful. If no old stars existed, the argument for extraordinary youth would become dramatically stronger. The galaxy's history effectively depended on a few faint points of light. That fact highlights something wonderful about astronomy. Enormous questions often depend on tiny details. The age of an entire galaxy, the evolution of cosmic structure, the behavior of star formation across billions of years. All of it might hinge on detecting stars so faint they barely appeared in telescope images. Fortunately, technology continued advancing. The Hubble Space Telescope had already transformed astronomy. Its observations provided unprecedented clarity, and researchers increasingly believe that Hubble possessed the capability to settle the argument. If ancient stars lurked within the Zwicky 18, Hubble had a realistic chance of finding them. If Hubble failed, the implications would become difficult to ignore. The anticipation surrounding those observations was considerable. Astronomers understood what was at stake. This wasn't merely a question about one dwarf galaxy. It was a test of broader ideas concerning galaxy evolution. Could galaxies remain youthful for billions of years? Could some systems preserve primitive conditions almost indefinitely? Were researchers missing something fundamental? By the time astronomers began arguing seriously about the age of Zwicky 18, one thing had become obvious. Nobody could simply ask the galaxy how old it was. That may sound like a ridiculous statement, but it highlights a genuine challenge in astronomy. When geologists want to determine the age of a rock, they can often collect a sample and analyse it directly. Archaeologists can excavate artifacts. Biologists can examine living organisms. Astronomers don't enjoy those advantages. Galaxies sit millions or billions of light years away. Nobody can travel there. Nobody can collect samples. Nobody can inspect them up close. Everything astronomers know about a galaxy comes from a surprisingly limited source. Light. Every conclusion, every measurement, every theory, every argument. It all begins with light reaching a telescope. The challenge is transforming that light into a history lesson. Fortunately, galaxies leave clues everywhere. They leave clues in their stars. They leave clues in their gas. They leave clues in their chemistry. They leave clues in their structure. The difficulty lies in learning how to read those clues correctly. In many ways, astronomers function as cosmic detectives. A detective investigating a century-old mystery cannot witness the original events. Instead, they examine evidence left behind. A galaxy presents the same situation. Astronomers cannot observe billions of years of evolution directly. Instead, they reconstruct the past from what remains visible today. This process becomes especially important when studying unusual objects like I Zwicky 18. If researchers wanted to know whether the galaxy was genuinely young, they first needed reliable methods for measuring galactic age, and that turns out to be far more complicated than measuring the age of a star. A single star often provides relatively straightforward clues. Galaxies are different. A galaxy contains many stars, sometimes millions, sometimes billions, sometimes hundreds of billions. Those stars formed at different times. They evolved differently. Some died long ago, others formed recently. A galaxy is not one object with one age. It is a collection of countless objects, each contributing to a larger story. Asking how old a galaxy is can therefore be surprisingly tricky. Do we mean the age of its oldest stars? The age of most of its stars? The age of its current structure? The age of its latest burst of star formation? Astronomers must answer all of those questions separately. Consider a city. Imagine trying to determine the age of a city like Rome. Do you measure from the oldest surviving building, the founding date, the average age of existing structures, the newest district? Each approach produces a different answer. Galaxies present a similar challenge. Their histories stretch across billions of years. Different components preserve evidence from different periods. That is why astronomers rely on multiple techniques rather than a single measurement. One of the most important methods involves studying stellar populations. This approach became central to the investigation of the Zwicky 18. The basic idea is surprisingly simple. Stars change predictably as they age. Unlike people, stars do not become wrinkled or complain about their backs. Instead, they change temperature, brightness, size, colour, internal structure. These changes follow well-understood patterns. Astronomers have spent more than a century studying stellar evolution. As a result, they know what stars should look like at different stages of their lives. This knowledge allows researchers to estimate ages, not always perfectly, not always precisely, but often with remarkable accuracy. Imagine visiting a school playground. Without asking anyone's age, you could probably identify toddlers, children, teenagers, and adults. Their characteristics differ. Stars work similarly. Astronomers can identify youthful stars, mature stars, and ancient stars by examining their properties. When large numbers of stars are analysed together, the age distribution begins revealing the history of an entire galaxy. This process relies heavily on one of astronomy's most powerful tools, the Hertzsprung-Russell diagram. The name sounds intimidating. The concept is not. The diagram plots stars according to brightness and temperature. Different types of stars occupy different regions. As stars evolve, they move through those regions in predictable ways. The result resembles a cosmic family portrait. Every star's position provides information about its stage of life. When astronomers create such diagrams for entire stellar populations, patterns emerge. Those patterns reveal age. Suppose a galaxy contains mostly hot, massive stars. That would suggest recent star formation. Massive stars live fast and die young. Many survive only a few million years. Finding large numbers of them indicates that star formation occurred recently. Now imagine a different galaxy dominated by smaller, cooler stars. Many of those stars can survive for billions of years. Their presence suggests a much older population. The comparison becomes even more powerful when multiple generations coexist. Most galaxies contain stars of various ages. Young stars reveal recent activity. Older stars reveal ancient history. Together, they create a timeline. This method works remarkably well when astronomers can resolve individual stars. Unfortunately, that is not always possible. Distance creates problems. A nearby galaxy allows researchers to distinguish individual stars clearly. A distant galaxy often appears as a blended mass of light. Individual stars disappear into the crowd. Studying I Zwicky 18 required observations right at the edge of what technology could accomplish. At roughly 59 million light-years away, the galaxy was close enough to study in detail, but far enough to remain challenging. Researchers needed exceptional instruments, exceptional data, exceptional patience. Yet stellar populations represented only one approach. Astronomers also investigate chemical composition. This method played a major role in the I Zwicky 18 debate. Every generation of stars alters a galaxy's chemistry. The earliest universe contained mostly hydrogen and helium. Heavy elements were rare. Stars gradually changed that situation. Inside stellar cores, nuclear fusion created heavier elements: carbon, oxygen, nitrogen, silicon, iron, and many others. When stars died, those materials entered surrounding space. Future generations inherited them. The process repeated endlessly. Over time, galaxies became increasingly enriched. This means chemistry acts like a historical record. A galaxy rich in heavy elements generally experienced extensive star formation over long periods. A galaxy poor in heavy elements may have undergone less chemical evolution. The logic seems straightforward, and in many cases it works beautifully. Yet chemistry can sometimes be deceptive. That realization became crucial when studying I Zwicky 18. The galaxy possessed extraordinarily low metallicity, among the lowest ever observed. At first glance, this suggested youth. Fewer heavy elements implied fewer generations of stars. Fewer generations implied a shorter history. Simple, except galaxies rarely behave simply. Gas can flow into galaxies from surrounding space. That incoming gas may dilute existing chemical enrichment. Galaxies can also lose enriched gas through powerful stellar winds and explosions. Chemical evolution therefore depends on more than age alone. Environment matters, history matters, chance matters. A galaxy can appear chemically primitive even after billions of years under the right circumstances. Astronomers understood this possibility, which is why chemistry alone could not settle the debate. Another important technique involves measuring star formation rates. Galaxies do not form stars at constant rates forever. Activity rises and falls. Some periods resemble construction booms, others resemble economic recessions. A galaxy experiencing intense star formation often appears dramatically different from one in a quiet phase. Researchers can estimate current star formation by examining specific wavelengths of light. Young massive stars produce enormous amounts of ultraviolet radiation. That radiation influences surrounding gas clouds. Certain emission lines become visible. These signatures allow astronomers to estimate how rapidly new stars are forming. I Zwicky 18 displayed vigorous activity. Bright star-forming regions dominated observations. The galaxy appeared energetic, youthful, busy. Yet astronomers knew that appearances can be misleading. A galaxy undergoing a temporary burst of activity can look much younger than it actually is. The challenge was distinguishing recent events from long-term history. Imagine meeting someone during the most exciting week of their life. You might gain a distorted impression of their normal routine. Galaxies can create similar misconceptions. Astronomers therefore needed deeper evidence. They needed indicators of ancient history, not merely current behavior. One of the most powerful indicators involves red giant stars. Red giants became central to the investigation of I Zwicky 18. Many stars eventually enter this stage late in life. They expand enormously. Their outer layers cool. They become brighter and redder. Importantly, red giants often signal the presence of older stellar populations. Finding them can reveal ancient history hidden beneath younger stars. For years, astronomers searched for such evidence inside I Zwicky 18. The results remained frustratingly ambiguous. Observations hinted at possibilities. Nothing seemed definitive. The galaxy refused to surrender its secrets easily. Meanwhile, theoretical models contributed additional insights. Modern astronomy relies heavily on computer simulations. Researchers create virtual galaxies and allow physical laws to shape their evolution. Gravity operates, gas collapses. Stars form. Chemical enrichment occurs. The resulting simulations provide expectations against which observations can be compared. These models suggested that genuinely young galaxies should be extraordinarily rare in the modern universe. The universe has simply existed too long. Most structures should have begun forming billions of years ago. Finding a truly young galaxy would therefore be exceptional, not impossible, but exceptional. Again, I Zwicky 18 occupied an uncomfortable position. The observation suggested one thing. The theoretical expectation suggested another. Neither side could claim complete victory. Another technique involves examining variable stars. Certain stars change brightness in predictable ways. These stars serve as valuable distance indicators. Knowing distance accurately is essential, because age estimates often depend on luminosity measurements. Errors in distance can affect conclusions. Astronomers therefore spent considerable effort refining measurements of I Zwicky 18's location. Every improvement strengthened confidence in subsequent analyses. Distance, chemistry, stellar populations, star formation rates, computer simulations. Each method contributed pieces of the puzzle. None provided a complete answer. That is often how science works. Popular culture sometimes portrays discoveries as dramatic moments of revelation. A scientist looks through a telescope. Everything becomes clear. Reality is usually slower. Evidence accumulates gradually. Confidence increases incrementally. Many small clues eventually combine into a larger picture. I Zwicky 18 represented exactly that kind of investigation. Researchers gathered evidence from every available source. Each measurement narrowed possibilities. Each observation eliminated certain explanations. The process required years, in some cases, decades. The galaxy became one of astronomy's most persistent mysteries because every method seemed to produce a slightly different story. Chemistry suggested youth. Theory suggested age. Appearance suggested youth. Expectations suggested age. The contradiction proved irresistible. Perhaps the most important lesson emerging from the investigation involved humility. Galaxies are extraordinarily complex systems. No single measurement tells the entire story. No single observation provides complete certainty. Astronomers must combine evidence from multiple sources. Only then can they reconstruct a reliable history. I Zwicky 18 forced researchers to do exactly that. It challenged assumptions, tested methods, exposed limitations. In many ways, it became a case study in how astronomical science actually operates, not through instant answers, through careful accumulation of evidence. And as increasingly powerful observations became available, one particular instrument began providing exactly the kind of information researchers needed: the Hubble Space Telescope. For years, astronomers had suspected that Hubble might finally reveal whether ancient stellar populations existed inside I Zwicky 18. If old stars were present, Hubble had a realistic chance of finding them. If they remained absent, the argument for genuine youth would grow dramatically stronger. The galaxy's history was about to face its most rigorous test yet, and the results would ultimately reshape how astronomers thought about one of the most unusual dwarf galaxies ever discovered. Long before astronomers could determine whether I Zwicky 18 was genuinely young, they became fascinated by something far easier to measure: its ingredients, not its stars, not its structure, not even its age, its raw material. Because when researchers examined the galaxy's composition, they found themselves staring at one of the most chemically primitive galaxies ever discovered. That statement might not sound especially dramatic at first. After all, galaxies are made of gas. Astronomers discover gas everywhere. Entire clouds of it drift between stars. Enormous reservoirs surround galaxies. Hydrogen is the most common element in the universe. Finding lots of hydrogen should hardly be surprising. Yet in the case of the Zwicky 18, the proportions were extraordinary. The galaxy seemed to contain remarkably little of anything else. Very little oxygen, very little carbon, very little nitrogen, very little iron, very little of the heavier elements astronomers collectively call metals. Once again, that word can sound strange. To an astronomer, oxygen counts as a metal. Carbon counts as a metal, even though nobody is building oxygen bridges or carbon spoons. In astronomy, anything heavier than hydrogen and helium falls into the metal category. The distinction matters because metals act as historical records. They reveal what happened inside a galaxy over time. To understand why, we need to return briefly to the early universe. Immediately after the Big Bang, the universe was remarkably simple. Hydrogen dominated. Helium came second. A tiny amount of lithium existed. That was essentially it. The periodic table familiar to modern chemistry did not yet exist. No oxygen, no carbon, no silicon, no iron. Those elements would have to be manufactured later. Stars became the factories responsible for that work. Deep inside stellar cores, nuclear fusion transforms lighter elements into heavier ones. Hydrogen becomes helium. Helium eventually contributes to the production of heavier materials. Massive stars continue the process further, creating increasingly complex elements throughout their lives. When those stars die, they return much of that material to surrounding space. Some stars do this gently. Others explode spectacularly as supernovae. Either way, the result is similar. The surrounding galaxy becomes enriched. Future generations of stars inherit those materials. The process repeats again and again and again. Over billions of years, galaxies gradually become more chemically sophisticated. In a sense, they become more experienced. A young galaxy should contain relatively few metals. An old galaxy should contain more. Not because age directly creates metals, because age provides time for generations of stars to manufacture them. This principle has become one of astronomy's most useful tools. Researchers can examine a galaxy's chemistry and estimate aspects of its evolutionary history. The method isn't perfect. Nothing in astronomy is. But it often works remarkably well. And that is why I Zwicky 18 immediately attracted attention. Its metallicity was astonishingly low. Among the lowest ever measured in a star-forming galaxy. Some estimates suggested oxygen abundances roughly 30 to 50 times lower than those found in the Milky Way. That is an enormous difference. Imagine visiting two cities. One contains thousands of years of architecture layered upon itself, ancient foundations, medieval streets, modern buildings, historical monuments. The other appears strangely untouched by comparison. Much of the expected development seems absent. You would naturally wonder why. Astronomers experienced a similar reaction. The galaxy looked chemically primitive, almost inexperienced, almost as though billions of years of stellar activity had somehow failed to leave their usual fingerprints. For researchers searching for evidence of youth, this observation seemed enormously significant. A galaxy containing so few heavy elements might indeed be young. Perhaps only a few generations of stars had existed there. Perhaps the process of chemical enrichment had barely begun. The possibility was difficult to ignore. Yet astronomy rarely rewards simple conclusions. The deeper researchers investigated, the more complicated the situation became. One reason involved understanding how metallicity actually changes over time. People sometimes imagine galaxy evolution as a straightforward progression. Start with hydrogen, form stars, create metals, repeat until the galaxy becomes chemically rich. Reality is considerably messier. Galaxies are not sealed containers. Material constantly moves. Gas flows inward. Gas flows outward. Galaxies interact with their environments. Some lose enormous amounts of enriched material. Others gain fresh supplies of primitive gas. The result resembles a city receiving new residents while simultaneously losing old ones. Population changes become more complicated than a simple count. Chemical evolution works similarly. A galaxy can remain metal poor for reasons unrelated to age. This realization became increasingly important when discussing I Zwicky 18. Suppose a galaxy experiences bursts of star formation separated by long, quiet periods. Metal production may proceed slowly. Suppose powerful stellar explosions eject enriched gas into intergalactic space. Chemical enrichment becomes less efficient. Suppose fresh hydrogen continuously flows into the system. Existing metals become diluted. Again, enrichment slows. Multiple pathways can produce low metallicity. Youth represents only one possibility. Nevertheless, the numbers associated with I Zwicky 18 remained remarkable. Researchers continued comparing it with other galaxies. Again and again the galaxy stood out. Many dwarf galaxies possess relatively low metallicities. That alone isn't unusual. Small galaxies often struggle to retain enriched gas. Their weaker gravity allows material to escape more easily. I Zwicky 18, however, occupied the extreme end of the distribution. It wasn't merely metal poor, it was extraordinarily metal poor. The galaxy seemed to preserve conditions rarely observed in the nearby universe. This characteristic generated excitement for another reason. Low metallicity galaxies offer valuable windows into cosmic history. The earliest galaxies formed from nearly pristine hydrogen and helium. Researchers cannot easily study those ancient systems in detail because they lie billions of light years away. Their light is faint. Their structures are difficult to resolve. Their individual stars remain invisible. A nearby low metallicity galaxy provides an alternative opportunity. Instead of observing the early universe directly, astronomers can examine environments resembling those ancient conditions. The comparison isn't perfect. No nearby galaxy truly exists in the early universe, yet some may preserve certain characteristics associated with that era. I Zwicky 18 quickly became one of the best candidates. Scientists began viewing it as a potential laboratory for studying primitive galactic environments. The galaxy offered something unusual: accessibility. Not easy accessibility, of course. Nobody was planning a field trip, But compared with galaxies billions of light years away, I Zwicky 18 sat practically next door. Researchers could investigate it with far greater detail. That opportunity proved irresistible. As observations accumulated, astronomers studied not only the stars but also the galaxy's gas. Gas dominates much of the system. Enormous clouds of hydrogen surround active star-forming regions. These clouds provide the raw material from which future stars will emerge. By analysing light emitted from ionized gas, researchers measured chemical abundances with increasing precision. The results consistently pointed toward the same conclusion. The galaxy remained exceptionally primitive. At first, some scientists interpreted this as evidence supporting genuine youth. The logic seemed straightforward. Few metals imply few generations of stars. Few generations imply limited history. Limited history implies youth, simple, elegant, potentially revolutionary. Yet other researchers remained cautious. History had taught astronomers an important lesson. Nature often creates shortcuts that mimic expected outcomes. A galaxy might look young without actually being young. It might appear primitive despite a long history. Observations alone could not immediately distinguish between those possibilities. One interesting clue emerged from comparisons with the Milky Way. Our galaxy contains stars spanning a vast range of ages. Some formed recently, others formed more than 12 billion years ago. The Milky Way has undergone extensive chemical evolution. Consequently, many regions contain relatively high metallicities. Planets like Earth owe their existence to that enrichment. Without previous generations of stars producing heavier elements, rocky planets could not form. Neither could human beings. Every carbon atom in your body, every oxygen atom you breathe, every calcium atom in your bones, all originated inside stars. The Milky Way's long history made such complexity possible. I Zwicky 18 appeared very different. If Earth somehow existed there, which it almost certainly does not, the environment would be dramatically altered. Heavy elements would be scarce. Planet formation would be more difficult. The galaxy's chemistry would resemble a much earlier stage of cosmic evolution. That realization fascinated researchers. Studying I Zwicky 18 was almost like examining a surviving relic from another era. Not because the galaxy literally travelled through time, because certain aspects of its composition resembled conditions common billions of years ago. The analogy is imperfect but useful. Imagine discovering a remote village preserving technologies and customs abandoned elsewhere centuries ago. The village itself would be modern. The people would be modern. Yet some characteristics might resemble earlier periods of history. Astronomers increasingly wondered whether I Zwicky 18 occupied a similar position in galactic evolution. Perhaps it wasn't young. Perhaps it simply evolved unusually slowly. That distinction became increasingly important. Meanwhile, researchers examined another intriguing possibility. What if the galaxy continuously received fresh supplies of hydrogen from outside? Intergalactic space contains enormous reservoirs of gas. Galaxies do not exist in isolation. Material flows through the cosmic web connecting large-scale structures. If I Zwicky 18 regularly accreted primitive hydrogen, that inflow could help explain its low metallicity. New gas would dilute existing heavy elements. The galaxy would appear chemically younger than its true age. Observations eventually revealed evidence supporting some version of this idea. Large amounts of neutral hydrogen surrounded the galaxy, more than enough to fuel future star formation. The system appeared rich in raw material. That abundance suggested an important possibility. The galaxy might not be newly formed. Instead, it might still possess access to resources that many galaxies exhausted long ago. This interpretation shifted the discussion. The question became less about age and more about evolutionary pace. Some galaxies race through their development. Others proceed slowly, very slowly. Perhaps I Zwicky 18 belonged to the second category. The comparison with human communities can be helpful. Two towns founded on the same day may look completely different centuries later. One becomes a major city, the other remains small and relatively unchanged. Age alone does not determine appearance. History matters, environment matters, opportunities matter, galaxies behave similarly. They share common origins but follow different paths. The more researchers studied I Zwicky 18, the more this perspective gained support. Yet uncertainty remained. The galaxy's chemistry still demanded explanation. Its metallicity remained extraordinarily low. Its star-forming regions remained intensely active. Its appearance remained youthful. Researchers needed additional evidence. Chemistry alone could not solve the mystery. They needed direct information about stellar populations. Specifically, they needed answers to a question that had haunted discussions of I Zwicky 18 for years. Were ancient stars actually present, orbiting hundreds of kilometers above Earth, far beyond clouds, storms, and the constant turbulence of our atmosphere? The Hubble Space Telescope had already transformed astronomy long before it turned its attention toward the Zwicky 18. It had photographed distant galaxies, measured the expansion of the universe, observed the birth and death of stars, captured images that would become some of the most recognizable scientific photographs ever taken. By the late 1990s and early 2000s, astronomers understood that Hubble possessed something they desperately needed for the I Zwicky 18 mystery: resolution. Not just better images, not merely prettier images, sharper images. The kind of clarity capable of separating individual stars inside distant galaxies. And that distinction mattered enormously. For years, the debate had revolved around a deceptively simple question. Where were the old stars? If ancient stellar populations existed inside I Zwicky 18, they would strongly suggest that the galaxy itself was old, perhaps unusual, perhaps chemically primitive, perhaps evolving more slowly than expected, but old. If those stars were absent, however, astronomers would be forced to consider far more dramatic possibilities. The galaxy might truly represent something extraordinarily rare. The stakes were high. Researchers weren't merely studying a small dwarf galaxy. They were testing assumptions about how galaxies evolve across billions of years, and the only way forward was to look deeper than anyone had managed before. The challenge involved the galaxy's distance. At roughly 59 million light-years away, I Zwicky 18 sits in an awkward observational territory, close enough that astronomers can study it in detail, far enough that individual stars remain difficult to resolve. Ground-based telescopes had provided valuable information. They revealed active star formation. They measured metallicity. They mapped gas clouds. Yet the crucial evidence remained frustratingly uncertain. Old stars, if present, appeared faint, very faint. The younger stars dominated observations. Bright blue stars flooded images with light. Massive star-forming regions attracted immediate attention. The ancient stellar population, if it existed, remained hidden beneath that brilliance. Imagine trying to identify elderly spectators sitting in the upper rows of a stadium while fireworks explode overhead. The fireworks are impossible to ignore. They dominate the scene. The quieter details become difficult to distinguish. That was essentially the problem facing astronomers. I Zwicky 18 contained spectacularly bright young stars. Those stars made it harder to detect the subtle evidence researchers needed. Hubble offered a solution. Operating above Earth's atmosphere, it avoided the blurring effects that limit ground-based observations. Every image emerged sharper, cleaner, more precise. Stars that previously merged together could now be separated. Tiny differences became visible, and that opened an entirely new chapter in the investigation. The first major observations generated tremendous excitement. Researchers immediately began analysing the galaxy's stellar populations in unprecedented detail. They weren't searching for gas. They weren't searching for chemical signatures. They were searching for individual stars. specifically stars old enough to prove that the galaxy possessed a long history. The work required patience. Astronomy often rewards patience. Images must be processed. Measurements must be checked. Potential sources of error must be investigated. Exciting claims demand careful verification. Scientists understood the importance of getting this right. If they announced the discovery of ancient stars, they needed confidence. If they announced their absence, they needed even more confidence. The consequences would be significant either way. As data accumulated, researchers began identifying different stellar populations throughout the galaxy. Young stars remained obvious. Nobody doubted their existence. The galaxy was actively forming stars. That fact had never been in question. The real challenge involved identifying much older populations hidden within the background. One group of stars became especially important: red giant stars. These stars represent a later stage of stellar evolution. Many stars eventually expand and cool after exhausting much of their fuel. Their brightness and colour make them useful markers for older stellar populations. Finding red giants inside I Zwicky 18 would provide powerful evidence that ancient stars existed there. The search intensified. Astronomers examined images repeatedly. Statistical analyses followed. Researchers compared observations against theoretical models. Gradually, evidence began emerging, subtle at first, then increasingly convincing. There appeared to be stars occupying precisely the region where red giants should appear. This was not the dramatic revelation many people imagine when they think about scientific discoveries. Nobody looked through a telescope and immediately shouted, "There they are!" Instead, confidence grew slowly. Measurement by measurement, study by study, paper by paper. The evidence pointed toward a conclusion many astronomers had suspected all along. Ancient stars were present. That finding changed everything. Or perhaps more accurately, it changed the question. The debate was no longer centered on whether I Zwicky 18 contained old stars. The evidence increasingly suggested that it did. The galaxy could no longer be interpreted as a completely newborn system. Its history extended much further into the past than some earlier proposals had suggested. Yet the mystery did not disappear. In many ways, it became more interesting. Because now astronomers faced a different challenge. If the galaxy contained ancient stars, why did it still look so young? Why did its chemistry remain so primitive? Why did it continue resembling galaxies from a much earlier era? Those questions proved surprisingly difficult to answer. Science often works this way. Solving one mystery reveals another. The discovery of old stars eliminated the most extreme interpretation. I Zwicky 18 was probably not a galaxy that had formed recently, but it remained extraordinarily unusual. Researchers continued investigating. Hubble observations revealed additional details. The galaxy appeared to contain stellar populations spanning different ages. Some stars were very young, others were much older. This pattern resembled what astronomers expected from a galaxy with a long history rather than a newly formed one. Yet the distribution remained unusual. The galaxy seemed to have experienced significant bursts of star formation rather than maintaining a steady pace. Periods of intense activity alternated with quieter intervals. That behaviour offered important clues. Perhaps I Zwicky 18 had evolved differently from larger galaxies. Perhaps its small size played a role. Dwarf galaxies often follow complicated evolutionary paths. Their weaker gravity makes them more vulnerable to disruption. Gas can escape more easily, star formation can become more erratic. External influences can have larger effects. The galaxy's unusual characteristics might therefore reflect its environment rather than its age. Researchers increasingly explored that possibility. Meanwhile, Hubble continued providing deeper observations. Longer exposure times revealed fainter stars. Improved instruments expanded capabilities further. Each new dataset refined the picture. The evidence for an ancient stellar population became stronger. The idea of a completely young galaxy gradually lost support, not because the galaxy wasn't unusual, because the observations pointed elsewhere. One particularly important result involved estimates of stellar ages. Some stars inside I Zwicky 18 appeared billions of years old, not millions, billions. That distinction mattered enormously. A galaxy containing stars several billion years old could not reasonably be described as newly formed. Its history stretched back deep into cosmic time. The galaxy had existed through enormous periods of the universe's evolution. It had witnessed events spanning much of cosmic history. In practical terms, the verdict was becoming clear. I Zwicky 18 was not the youngest galaxy in existence, at least not literally. Yet the galaxy remained one of the most chemically primitive systems ever observed nearby. That fact required explanation. Researchers began shifting their attention toward evolutionary history rather than absolute age. Perhaps the galaxy evolved unusually slowly. Perhaps it experienced long periods of inactivity. Perhaps inflows of fresh hydrogen continually diluted heavier elements. Perhaps powerful stellar winds removed enriched gas. Multiple mechanisms could contribute. The challenge involved determining which combination best matched observations. As theoretical models improved, astronomers started constructing more detailed evolutionary scenarios. The galaxy likely began forming stars billions of years ago. Not recently. However, its development proceeded differently from many larger galaxies. Star formation may have remained relatively inefficient. Chemical enrichment may have progressed slowly. Large reservoirs of hydrogen may have persisted throughout much of its history. Together, these factors could preserve youthful characteristics despite great age. The emerging picture was fascinating because it highlighted an important lesson. Age and appearance are not always the same thing. A galaxy can be old while looking young. It can possess ancient stars while maintaining primitive chemistry. It can preserve conditions that resemble earlier eras of cosmic history. I Zwicky 18 appeared to embody exactly that situation. The discovery transformed the galaxy from one mystery into another. Instead of asking whether it was young, researchers began asking why it looked young. The distinction seems subtle. Scientifically, it is profound. Imagine discovering a person who somehow retained many characteristics associated with youth, despite advanced age. The interesting question would no longer involve their birth date. It would involve understanding how they remained so unusual. Astronomers approached I Zwicky 18 similarly. The galaxy's true significance shifted. It was no longer important because it might be newly born. It became important because it preserved conditions rarely found in the modern universe. In some respects, that outcome proved even more valuable. A nearby galaxy resembling ancient systems provides an extraordinary laboratory. Researchers can study processes that were once common, but have since become rare. They can investigate low metallicity environments. They can observe star formation under primitive conditions. They can explore questions that would otherwise require examining galaxies billions of light years away. The galaxy became a bridge between past and present, not literally. Not through time travel, through preservation. Certain aspects of its environment appeared to retain characteristics associated with much earlier cosmic eras. That made it exceptionally useful. As the years passed, additional observations from Hubble continued refining our understanding. New instruments improved sensitivity. New analyses improved accuracy. The overall conclusion remained remarkably consistent. Ancient stars existed. The galaxy was old, yet it remained chemically primitive and unusually youthful in appearance. The debate had evolved. The most extreme interpretation faded. A more nuanced understanding emerged. And like many scientific discoveries, the final answer proved more complicated than either side initially expected. The galaxy wasn't the newborn cosmic city some researchers once imagined. Nor was it merely an ordinary dwarf galaxy behaving exactly as expected. It occupied an unusual middle ground. Old in age, young in character, ancient in origin, and primitive in composition. That combination transformed I Zwicky 18 into one of the most valuable dwarf galaxies in astronomy. Not because it overturned everything researchers thought they knew, because it demonstrated that galactic evolution can follow surprisingly diverse paths. Step outside the Milky Way for a moment and imagine that somehow you could visit I Zwicky 18 in person, not merely observe it through a telescope, not study it from millions of light years away, actually travel there. What would you find? What would the night sky look like? What would the stars be like? How different would daily existence feel inside one of the most chemically primitive galaxies ever discovered? These questions might sound like science fiction, but they help illuminate why astronomers find I Zwicky 18 so fascinating. A galaxy is more than a collection of measurements, more than metallicity values, more than star counts and emission lines. A galaxy is an environment. A place where stars form, where gas moves, where gravity shapes everything. An understanding that environment often reveals as much as understanding its age. The first thing a visitor would notice is size, or rather, the lack of it. Compared with the Milky Way, I Zwicky 18 is tiny. The Milky Way stretches roughly 100,000 light-years across and contains hundreds of billions of stars. I Zwicky 18 belongs to the category of dwarf galaxies. Its stellar population is dramatically smaller. Its physical dimensions are much more modest. Its overall structure lacks the immense scale that defines large spiral galaxies. If the Milky Way resembles a vast continent, I Zwicky 18 resembles a small island. Yet small does not mean simple. In many ways, dwarf galaxies can be more chaotic than larger systems. Large galaxies often develop organized structures, spiral arms, bulges, disks. Clear patterns emerge. Dwarf galaxies frequently look irregular, messier, less settled. I Zwicky 18 certainly falls into that category. Rather than displaying graceful spiral arms, it appears clumpy and uneven. Bright regions of star formation dominate the galaxy. Gas clouds occupy significant portions of its structure. The overall impression is one of activity rather than order. Imagine flying over a rapidly growing town where construction projects are happening everywhere simultaneously. That comparison comes surprisingly close. One of the defining characteristics of I Zwicky 18 is its active star formation. Stars are being born there right now. Massive clouds of hydrogen continue collapsing under gravity. New stars ignite. Radiation floods surrounding regions. The process remains ongoing. For astronomers, this activity is enormously valuable because it allows them to observe star formation in an environment unlike most nearby galaxies. The chemistry of the galaxy changes everything. Here on Earth, and throughout much of the Milky Way, heavy elements are relatively common, not everywhere, not equally distributed, but common enough that they influence nearly every aspect of astrophysics. In I Zwicky 18, the situation is different. Heavy elements remain scarce. Hydrogen dominates. The galaxy resembles a much earlier stage of cosmic evolution. That difference affects how stars form. It affects how gas behaves. It even affects how light interacts with matter. If you could somehow compare two giant molecular clouds, one in the Milky Way and one in I Zwicky 18, you would discover important differences in their composition. The cloud inside I Zwicky 18 would contain far fewer heavy elements, less oxygen, less carbon, less nitrogen, less of almost everything beyond hydrogen and helium. That primitive chemistry creates conditions more similar to those found billions of years ago. Astronomers often describe I Zwicky 18 as a nearby analogue for early galaxies precisely because of this characteristic. Not because it literally exists in the past, because certain environmental conditions resemble those that were common when the universe was much younger. Another striking feature involves the stars themselves. Many of the brightest stars in I Zwicky 18 are massive, hot and short-lived. These stars dominate observations because they shine so intensely. Blue-white light pours from star-forming regions. ultraviolet radiation floods surrounding gas. The galaxy often appears youthful because these stars command attention. Massive stars live dramatically. They consume fuel at astonishing rates. A star several times more massive than the Sun may burn through its resources hundreds or thousands of times faster. The result is brilliance. The price is longevity. Many survive only a few million years. On cosmic timescales, that is barely any time at all. If you lived inside I Zwicky 18 near one of these star-forming regions, the sky would likely appear spectacular. Clusters of bright young stars would dominate your view. Nebulous clouds of glowing gas would surround many of them. The scenery might resemble some of the most active star-forming regions observed within our own galaxy, except spread throughout an environment with dramatically different chemistry. The radiation levels would also be significant. Massive stars produce enormous amounts of ultraviolet light. That energy shapes surrounding gas clouds. It influences future star formation. It creates bubbles and cavities throughout the interstellar medium. Life as we know it would face challenges near such regions. Not necessarily impossible challenges, but substantial ones. Then again, discussing life inside I Zwicky 18 requires caution. Astronomers currently have no evidence of life there. In fact, primitive chemistry raises interesting questions about habitability. Heavy elements play crucial roles in planet formation. Rocky planets require elements such as silicon, oxygen, magnesium, and iron. Without sufficient quantities of these materials, constructing Earth-like worlds becomes more difficult. This doesn't mean planets cannot exist in I Zwicky 18. It means the process may differ significantly from what occurred in the Milky Way. Planetary systems could be rarer. Rocky planets could be less common. The entire architecture of planetary formation might look different. Researchers continue investigating these possibilities in low metallicity environments. The answers remain uncertain. One thing is clear, however. The galaxy offers a glimpse into conditions unlike those found throughout much of our cosmic neighbourhood. Gas dominates much of the story. Astronomers estimate that I Zwicky 18 contains substantial reservoirs of hydrogen. This hydrogen serves as the fuel for future generations of stars. In some respects, the galaxy appears rich in potential. Large amounts of raw material remain available. The system has not exhausted its resources. That fact helps explain why star formation continues. Many galaxies gradually consume or lose significant portions of their gas over time. Star formation slows, activity declines. I Zwicky 18 still possesses abundant supplies. The galaxy remains capable of producing new stars for a long time. That abundance contributes to its youthful appearance. It still behaves like a galaxy actively building itself. Not because it recently formed, because development remains ongoing. Another important aspect of daily life inside such a galaxy would involve the appearance of the night sky. This question fascinates both astronomers and the public, because skies vary dramatically depending on location. The night sky above Earth reflects our position within the Milky Way. Certain constellations appear familiar, certain star fields dominate. The galactic disk stretches across the heavens as a faint band. Inside I Zwicky 18, everything would be different. The arrangement of stars would change completely. Constellations would not exist. The Milky Way itself would appear as a distant external galaxy. Assuming you occupied a suitable location and possessed a sufficiently dark sky, you might see our galaxy as a faint island of light among countless others. That thought is always worth considering. From our perspective, the Milky Way feels enormous. It surrounds us, defines our cosmic home. Yet from another galaxy, it becomes just one more object in the distance, one more member of an immense population. Perspective changes everything. The density of stars would vary significantly depending on your location within I Zwicky 18. Near active star-forming regions, the sky could appear crowded and brilliant. Elsewhere, enormous dark spaces might separate stellar concentrations. Unlike the organised disk of the Milky Way, dwarf galaxies often possess more irregular distributions. Travelling through the system could produce dramatic changes in appearance. Some regions would feel bustling, others relatively empty. The galaxy's gravitational environment would differ as well. Dwarf galaxies possess far less mass than giant spirals. Their gravitational influence remains weaker. This affects everything from gas dynamics to orbital motion. Stars still orbit. Gravity still dominates large-scale behaviour, yet the overall structure remains more fragile. Interactions with neighbouring galaxies can have larger consequences. Gas flows become more significant. External influences matter more. This vulnerability may help explain some of I Zwicky 18's unusual characteristics. Small galaxies often lead complicated lives. The Milky Way can absorb disturbances relatively easily. A dwarf galaxy may respond much more dramatically. Researchers suspect that interactions, gas accretion and environmental effects all contributed to I Zwicky 18's history. The galaxy did not evolve in isolation. Few galaxies truly do. Its surroundings influenced its development influenced its appearance, and its appearance ultimately contributed to the decades-long mystery surrounding its age. One particularly interesting aspect of life inside I Zwicky 18 involves timescales. Human beings naturally think in years, perhaps decades, sometimes centuries. Galaxies operate differently. The star-forming regions visible today may evolve dramatically over millions of years. Gas clouds collapse. Massive stars explode. New generations emerge. Entire regions transform. What appears stable during a human lifetime may actually represent a temporary phase. This realization helps explain why astronomers hesitate to describe galaxies using simple labels: young, old, active, inactive. Such terms often conceal tremendous complexity. I Zwicky 18 demonstrates that complexity beautifully. The galaxy contains ancient stars, yet it remains actively productive. It contains primitive chemistry, yet it has existed for billions of years. It appears youthful, yet it possesses a long history. Those contradictions make more sense when viewed from inside the environment itself. The galaxy is not frozen. It is evolving, slowly, continuously, following a path different from many larger systems. Perhaps that is the most important lesson. For years, researchers hoped to determine whether I Zwicky 18 was young or old. The answer turned out to be more nuanced. The galaxy is old enough to contain ancient stars, yet it retains characteristics associated with much earlier periods of cosmic history. Living inside such a galaxy would feel like inhabiting a place where some aspects of development progressed normally, while others lagged behind. Not primitive in every respect, not modern in every respect, something in between. A system preserving valuable clues about how galaxies behave under unusual conditions, and those clues extend far beyond the galaxy itself. Because once astronomers realized that I Zwicky 18 could act as a nearby analogue for ancient galactic environments, attention naturally shifted toward a much larger question. If this small dwarf galaxy resembles conditions common billions of years ago, what exactly can it teach us about the early universe itself? Few galaxies have earned a reputation quite like I Zwicky 18. Not because it is large, not because it is especially bright, not because it dominates astronomy textbooks in the way some famous galaxies do. Its importance comes from something far more unusual. It offers astronomers a rare opportunity to study conditions that may resemble those found during one of the earliest periods of galactic history. In other words, it functions as a window, not a window through space alone, a window through time. This idea became increasingly important after Hubble observations revealed that the galaxy was not truly young. For a while, some researchers had hoped they might be looking at a galaxy that formed surprisingly late in cosmic history. The evidence eventually pointed elsewhere. Ancient stars existed. The galaxy possessed a long history. the case for a genuinely newborn galaxy weakened considerably. At first glance, that outcome might seem disappointing. A revolutionary discovery had become a more ordinary one. Except that wasn't what happened at all. In many respects, the galaxy became even more valuable. The reason is simple. Astronomers do not necessarily need a galaxy to be young in order to learn about the early universe. Sometimes all they need is a galaxy that resembles the early universe, and that distinction changed everything. To understand why, imagine trying to study life in an ancient civilization. Suppose the civilization itself vanished thousands of years ago. You cannot travel back in time. You cannot interview its inhabitants. You cannot observe their daily lives directly. Yet if you discovered a community that preserved some of the same technologies, materials and environmental conditions, you might gain useful insights. The community would not literally belong to the ancient world, but certain characteristics could help illuminate it. Astronomers increasingly began viewing I Zwicky 18 in a similar way. The galaxy is not an ancient relic frozen in time. It is a living galaxy existing in the present universe. Yet some of its properties resemble conditions that were common billions of years ago. That makes it extraordinarily useful. The early universe looked very different from the cosmos we see today. Modern galaxies have experienced billions of years of evolution. Countless generations of stars have formed and died. Heavy elements have accumulated. Structures have grown larger. Interactions and mergers have reshaped entire regions of space. The universe has become chemically richer and structurally more complex. The earliest galaxies existed before most of that happened. Their environments were simpler. Their chemistry was simpler. Their stars formed under very different circumstances. Understanding those ancient conditions remains one of astronomy's major goals. The challenge is that the earliest galaxies are extremely far away. When astronomers observe them, they are looking across enormous distances. 10 billion light years, 12 billion light years, sometimes even farther. Those observations are incredibly valuable. They allow researchers to witness the universe during its youth, yet they come with limitations. The galaxies appear faint. Details remain difficult to resolve. Individual stars cannot usually be distinguished. Researchers often see entire galaxies as tiny smudges of light. Important information remains hidden. I Zwicky 18 offers a different opportunity. The galaxy sits only about 59 million light-years away. That distance remains enormous by human standards. But in astronomy, it qualifies as relatively nearby. Nearby enough for detailed study. Nearby enough for astronomers to examine its stars, gas clouds and chemical composition far more thoroughly than would be possible for genuinely ancient galaxies. This combination of characteristics makes the galaxy uniquely valuable. Researchers can investigate a system with primitive properties while enjoying the observational advantages of proximity. The result resembles finding a nearby laboratory for studying conditions that otherwise exist only at immense distances. One of the most important similarities involves metallicity. The first galaxies formed from material containing very few heavy elements. Remember that the early universe consisted primarily of hydrogen and helium. Heavier elements had not yet been manufactured in significant quantities. Those elements emerged later through stellar evolution. Consequently, the first generations of galaxies existed in extremely metal-poor environments. I Zwicky 18 shares this characteristic. Its metallicity remains extraordinarily low, not quite as low as the very first galaxies, but low enough to provide valuable comparisons. This allows astronomers to investigate how stars behave in chemically primitive conditions. The question is more important than it might initially appear. Heavy elements influence many aspects of star formation. They affect cooling processes inside gas clouds. They alter stellar atmospheres. They influence how radiation interacts with surrounding material. Even small changes in chemical composition can produce significant consequences. Modern star formation occurs in environments enriched by billions of years of cosmic history. The first galaxies did not enjoy that advantage. Their stars formed under different rules. Studying I Zwicky 18 helps researchers explore what those differences might have looked like. Another reason the galaxy attracts attention involves its active star formation. The earliest galaxies spent much of their existence building stellar populations. Stars formed rapidly. Gas reservoirs remained abundant. Conditions changed continuously. I Zwicky 18 displays some similar characteristics. The galaxy still contains substantial amounts of hydrogen. Star formation remains active. Massive young stars dominate many regions. The system appears energetic and productive. That activity provides opportunities to study star formation in a primitive environment. Researchers can observe processes that may resemble those operating billions of years ago. Again, the comparison is not perfect. No nearby galaxy can exactly replicate the early universe. The broader cosmic environment has changed dramatically. The universe itself has aged. Large-scale structures have evolved. Countless generations of stars have enriched surrounding space. Nevertheless, certain similarities remain useful. Astronomy often advances through comparisons. Researchers identify systems sharing important characteristics. Those systems become laboratories for testing ideas. I Zwicky 18 excels in that role. Its unusual properties allow scientists to ask questions that would otherwise remain difficult to investigate. What happens when stars form in environments containing very few heavy elements? How efficiently does gas collapse? How do stellar winds behave? How rapidly does chemical enrichment occur? These questions matter because they connect directly to the earliest phases of galaxy evolution. One particularly interesting area of research involves massive stars. The first generations of stars in the universe were likely different from those forming today. Astronomers suspect many were extremely massive, perhaps far more massive than typical stars in the modern Milky Way. Their short lives influenced surrounding environments dramatically. They produced radiation, generated heavy elements, triggered further star formation, and eventually exploded. Understanding such stars remains difficult because none survive today. Massive stars burned fuel too quickly. They disappeared long ago. Yet low metallicity galaxies like I Zwicky 18 may offer clues. The stars forming there exist under conditions closer to those experienced by ancient stellar populations. By studying them carefully, researchers gain insight into processes that shaped the early universe. The galaxy therefore acts as a bridge between observation and theory. It helps connect modern measurements with ancient events. Another important connection involves reionization. This period represents one of the major transitions in cosmic history. Following the Big Bang, the universe eventually cooled enough for neutral hydrogen to dominate. Later, radiation from early stars and galaxies transformed much of that hydrogen. The process altered the state of the universe itself. Astronomers refer to this transformation as reionization. Understanding which objects contributed most remains an active area of research. Low metallicity galaxies may provide important clues. Systems resembling I Zwicky 18 could share characteristics with galaxies that participated in those ancient events. Studying them helps researchers refine models of cosmic evolution. The implications extend far beyond a single dwarf galaxy. In some respects, I Zwicky 18 functions as a natural experiment. Nature created an unusual environment. Astronomers gained the opportunity to observe it. The galaxy became a testing ground for ideas about star formation, chemical evolution, and galactic development. That opportunity is rare. The universe does not provide convenient laboratories on demand. Researchers must work with whatever examples nature offers. I Zwicky 18 happens to be one of the best examples available. As telescope technology improved, interest in the galaxy continued growing. The Hubble Space Telescope contributed enormously. More recently, the arrival of the James Webb Space Telescope expanded possibilities even further. Webb was specifically designed to investigate some of the earliest galaxies in existence. Its infrared capabilities allow it to peer deeper into cosmic history than previous observatories. As Webb studies distant galaxies, astronomers increasingly compare those observations with nearby systems like I Zwicky 18. The relationship works both ways. Ancient galaxies help researchers understand I Zwicky 18. I Zwicky 18 helps researchers understand ancient galaxies. Together they create a more complete picture. One fascinating realization emerged from these comparisons. Galactic evolution appears far more diverse than scientists once assumed. Early models often emphasized broad trends. Galaxies form. Galaxies grow. Galaxies enrich themselves chemically. While those processes remain correct, the details vary enormously. Some galaxies evolve rapidly, others evolve slowly. Some consume gas efficiently. Others preserve large reservoirs for billions of years. Some become chemically rich relatively quickly. Others remain primitive far longer than expected. Zwicky 18 belongs to that second category. The galaxy demonstrates that evolution can proceed at different speeds. That lesson matters because it improves theoretical models. Researchers cannot simply assume every galaxy follows the same path. Nature is more creative than that. The universe produces diversity. Studying unusual systems reveals that diversity and unusual systems often become disproportionately important, not because they represent the norm, because they reveal possibilities. A biologist learns a great deal from unusual organisms. A geologist learns a great deal from unusual landscapes. Astronomers learn a great deal from unusual galaxies. I Zwicky 18 belongs firmly in that category. Its value comes from the questions it raises. Questions about chemical evolution, questions about star formation, questions about how galaxies preserve primitive conditions, questions about what the early universe may have looked like. The galaxy does not answer all those questions by itself. No single object could. But it contributes critical evidence. It provides context. It offers comparisons. It allows researchers to test ideas that would otherwise remain speculative. Perhaps the most remarkable aspect of the story is how the galaxy's significance evolved. Initially, researchers became interested because they wondered whether it might be young. Eventually, they discovered something more subtle. The galaxy was old enough to contain ancient stars, yet it remained valuable precisely because it retained characteristics associated with much younger cosmic environments. In other words, its importance survived the disappearance of the original mystery. If anything, it increased. The galaxy transformed from a candidate for the youngest galaxy in the universe into one of the best nearby laboratories for studying how the earliest galaxies may have behaved. And as researchers continued examining its stars, gas and chemistry, another question naturally emerged. If I Zwicky 18 was not truly young, then what exactly should we call it? A galaxy that looks young but isn't. A galaxy that preserves primitive conditions despite a long history. A galaxy that resembles ancient systems while existing in the modern universe. Labels can be surprisingly powerful. Give something a name and people immediately begin building expectations around it. Call a mountain the tallest in the world, and everyone wants to know its height. Call a star the brightest in the sky, and attention immediately turns toward its luminosity. Call a galaxy the youngest in the universe, and suddenly one question overshadows all others. How young is it? For many years, that question dominated discussions surrounding I Zwicky 18. The galaxy became famous because it appeared to challenge the normal timeline of cosmic evolution. Its primitive chemistry attracted attention. Its intense star formation attracted attention. Its apparent lack of obvious ancient stellar populations attracted attention. Together, these characteristics created a compelling possibility. Perhaps astronomers had discovered a galaxy that formed much later than expected. Perhaps the universe still contained genuinely youthful galaxies, billions of years after most others had already matured. It was an exciting idea, a dramatic idea. And like many dramatic ideas in science, it proved to be only partially correct. As better observations accumulated, especially from the Hubble Space Telescope, the picture changed. Ancient stars appeared as evidence for long-term stellar populations strengthened. The galaxy could no longer be described as genuinely young in the literal sense. Its history stretched back billions of years. It had existed through a substantial fraction of cosmic history. The original mystery seemed solved, or at least that is what many people expected. Instead, the mystery evolved, because a new question immediately emerged. If the galaxy was old, why did it still look so young? That question turned out to be every bit as fascinating as the original one, in some respects, even more fascinating. Finding a young galaxy would have been surprising. Finding an old galaxy that convincingly imitates a young galaxy reveals something deeper. It suggests that galactic evolution may proceed along very different paths. It suggests that age alone does not determine appearance. It suggests that some galaxies mature differently than others, and that realization transformed the entire discussion surrounding I Zwicky 18. Astronomers gradually shifted their focus. The question was no longer whether the galaxy formed recently. The question became why it evolved so slowly. Because when researchers examined the evidence carefully, a remarkable pattern emerged. The galaxy appeared old. Yet many of the characteristics associated with maturity remained absent. Its metallicity remained extraordinarily low. Large reservoirs of hydrogen still existed. Star formation continued actively. Many regions retained primitive conditions rarely observed in nearby galaxies. The galaxy seemed to have spent billions of years developing more slowly than expected. Imagine visiting two towns founded on the same day centuries ago. One grows into a sprawling city. Its population expands. Its infrastructure becomes increasingly complex. Its landscape changes repeatedly. The other remains relatively small. Growth occurs, but at a slower pace. Certain features remain surprisingly unchanged. Both towns share a similar age, yet they look very different. Nobody would assume the smaller town was newly founded. Instead, they would conclude that its history followed a different trajectory. Astronomers increasingly reached a similar conclusion regarding I Zwicky 18. The galaxy was old. Its development simply followed an unusual path. That distinction matters enormously. Galaxies are often described using age-related language. Young galaxies, old galaxies, mature galaxies, ancient galaxies. These labels can be useful, but they sometimes oversimplify reality. Age and evolutionary state are not necessarily the same thing. A galaxy can be old while retaining primitive characteristics. It can be ancient while still appearing youthful. I Zwicky 18 demonstrated this beautifully. Researchers therefore began exploring the idea of delayed evolution. The phrase sounds technical. The concept is straightforward. The galaxy appears to have progressed through cosmic history more slowly than many of its peers. Not because time passed differently, not because it somehow escaped billions of years of cosmic history, because the processes driving galactic evolution operated differently. The challenge was identifying exactly why. One possibility involved star formation efficiency. Not all galaxies convert gas into stars at the same rate. Some are remarkably productive, others are less efficient. Suppose two galaxies begin with similar quantities of hydrogen. One rapidly transforms that hydrogen into stars, the other proceeds more slowly. After billions of years, the results could look dramatically different. The first galaxy becomes chemically enriched. The second retains much of its original material. Both share a similar age. Their appearances diverge. Researchers suspect something like this may have occurred in I Zwicky 18. The galaxy appears to have spent much of its history forming stars relatively inefficiently. As a result, chemical enrichment proceeded more slowly. Large reservoirs of hydrogen survived. Primitive conditions persisted. Another factor may involve the galaxy's size. Dwarf galaxies face challenges that larger systems often avoid. The Milky Way possesses substantial gravity. That gravity helps retain gas and heavy elements. When stars explode, much of the enriched material remains trapped within the galaxy. Dwarf galaxies operate under different circumstances. Their weaker gravity allows material to escape more easily. A powerful burst of star formation can eject significant amounts of gas into surrounding space. Heavy elements may leave the galaxy before future generations of stars can inherit them. The process effectively slows chemical evolution. Imagine trying to save money while someone repeatedly removes part of your income. Progress becomes difficult. Galaxies experience something similar when enriched material escapes. Astronomers believe this mechanism likely contributed to I Zwicky 18's unusual chemistry. Each generation of stars produced heavy elements, yet not all of those elements remained available for future enrichment. The galaxy may have repeatedly lost valuable material. Over billions of years, the effect becomes significant. Chemical maturity arrives more slowly. Environmental influences provide another possible explanation. Galaxies do not exist in complete isolation. Even seemingly lonely systems interact with their surroundings. Gas flows through intergalactic space. Material moves along the cosmic web. Galaxies exchange matter with their environments. Researchers increasingly suspect that I Zwicky 18 may have received fresh supplies of primitive hydrogen throughout its history. This process acts almost like dilution. Imagine adding pure water to a concentrated solution repeatedly. The overall concentration decreases. Similarly, fresh hydrogen entering a galaxy can dilute existing heavy elements. The galaxy remains chemically primitive despite ongoing stellar activity. Observations support aspects of this scenario. Large amounts of hydrogen surround I Zwicky 18. The galaxy appears rich in raw material. More importantly, that material remains relatively pristine. Fresh gas may have helped preserve youthful characteristics long after the galaxy itself ceased being young. This possibility fascinates astronomers because it reveals how complex galactic evolution can become. Simple models often assume gradual enrichment over time. Reality appears more complicated. Gas enters, gas leaves, stars form, stars explode. Multiple processes interact simultaneously. The resulting history can differ dramatically from one galaxy to another. I Zwicky 18 may represent an extreme example of this diversity. Its unusual characteristics forced researchers to reconsider certain assumptions. Not because existing theories were wrong, because they were incomplete. The galaxy demonstrated that evolution can proceed at very different speeds. Some systems race forward. Others move slowly, very slowly. Perhaps one of the most interesting aspects of the story involves perspective. Imagine showing two photographs to someone unfamiliar with astronomy. One image depicts a chemically rich spiral galaxy. The other shows I Zwicky 18. Many people would naturally assume the spiral galaxy was older. The assumption would seem reasonable. The spiral galaxy looks mature, organized, developed. I Zwicky 18 appears comparatively primitive, yet age alone would not justify that conclusion. The galaxy's history stretches back billions of years. It simply spent those billions of years following a different path. This realization mirrors situations encountered elsewhere in science. Evolution rarely follows a single route. Different environments produce different outcomes. Different histories produce different appearances. The same principle applies to galaxies. One of the reasons researchers remain fascinated by I Zwicky 18 is that it highlights this complexity so clearly. The galaxy resists simple classification. It is not young, yet it looks young. It is not primitive in every respect, yet it remains chemically primitive. It contains ancient stars, yet active star formation dominates its appearance. Each statement seems contradictory. Taken together, they describe reality remarkably well. The galaxy occupies a category that astronomers once struggled to recognize. An old galaxy preserving youthful characteristics, a mature system retaining primitive conditions, a nearby object resembling environments common much earlier in cosmic history. This perspective gradually replaced the original interpretation. Today, researchers generally do not describe I Zwicky 18 as the youngest galaxy in the universe. The evidence no longer supports that claim. Instead, many view it as one of the youngest-looking galaxies. The distinction may seem minor. Scientifically, it changes everything. The original mystery asked whether the galaxy formed recently. The modern mystery asks why it evolved differently. Why did it retain so much hydrogen? Why did metallicity remain so low? Why did enrichment proceed so slowly? Why does the galaxy still resemble systems from a much earlier era? Those questions continue driving research today, and unlike the original question, they connect directly to broader issues in galaxy evolution. Understanding delayed evolution helps astronomers understand diversity. It helps explain why galaxies develop differently. It improves theoretical models. It reveals pathways that might otherwise remain hidden. In that sense, the disappearance of the original mystery did not reduce the galaxy's importance. Quite the opposite. The more researchers learned, the more valuable the galaxy became, because nature had provided something unusual, not a newborn galaxy, something arguably more informative. An ancient galaxy that never quite grew up the way astronomers expected. Perhaps the most valuable scientific discoveries are not the ones that provide simple answers. Instead, they are the discoveries that force researchers to ask better questions. I Zwicky 18 belongs firmly in that category. When astronomers first became interested in the galaxy, they thought they might be investigating a straightforward mystery. Was this the youngest galaxy in the universe? It sounded like a question with two possible answers: yes or no. As often happens in science, reality proved considerably more complicated. The answer eventually became neither. The galaxy was not truly young, yet it was not behaving like a typical old galaxy either. The more researchers studied it, the more they realized that the real lesson had very little to do with finding the youngest galaxy. The real lesson involved understanding how differently galaxies can evolve. That realization extends far beyond a single dwarf galaxy sitting 59 million light-years away. It touches one of the most important ideas in modern astronomy. The universe is not a factory producing identical outcomes. Given similar starting conditions, galaxies can follow remarkably different paths. For many years, astronomers tended to think about galaxy evolution in relatively broad terms. Gas collapses, stars form, heavy elements accumulate, galaxies grow. The details vary, but the overall process remains similar. At a fundamental level, that picture is still correct. The problem is that nature rarely follows simple timelines. Some galaxies grow quickly, some grow slowly, some undergo violent mergers, others spend billions of years relatively undisturbed. Some consume their gas efficiently, others preserve enormous reservoirs of hydrogen long after astronomers expect them to. I Zwicky 18 demonstrated that these differences can become extreme. The galaxy effectively serves as a reminder that cosmic history is not a single story. It is billions of stories unfolding simultaneously. Imagine two children born on the same day. One grows up in a large city, the other grows up in a remote village. They experience different environments, different opportunities, different challenges. Years later, their lives may look dramatically different despite sharing the same age. Galaxies behave similarly. Age alone does not determine appearance. History matters, environment matters, interactions matter, chance matters. This understanding has become increasingly important as astronomers build more sophisticated models of cosmic evolution. Computer simulations have improved enormously during the last few decades. Modern simulations can follow billions of years of galactic development. Researchers include gravity, gas dynamics, star formation, dark matter, chemical enrichment, stellar explosions. The resulting virtual universes often reproduce many real observations remarkably well. Yet galaxies like I Zwicky 18 remain valuable because they test those models. Any theory capable of explaining galaxy evolution must also explain unusual galaxies, not merely the average cases, the exceptions, the outliers, the systems that refuse to behave as expected. In many scientific fields, unusual examples become disproportionately important. Biologists learn from unusual organisms, geologists learn from unusual landscapes, astronomers learn from unusual galaxies. The reason is simple. Ordinary examples confirm what researchers already suspect. Extraordinary examples reveal what they might be missing. I Zwicky 18 repeatedly played that role. Every time astronomers thought they understood its story, the galaxy revealed another layer of complexity. First came the question of age. Then came the question of delayed evolution. Then came questions involving gas accretion, chemical enrichment, and star formation efficiency. The galaxy kept expanding the conversation. One particularly important lesson involves metallicity. For decades, astronomers treated metallicity as one of the most useful indicators of galactic evolution. The logic seemed straightforward. Older galaxies should generally contain more heavy elements. Younger galaxies should generally contain fewer. The relationship remains useful today. Yet I Zwicky 18 demonstrated that the connection is not always simple. An old galaxy can maintain extraordinarily low metallicity under the right circumstances. Fresh hydrogen can enter the system. Enriched gas can escape. Star formation can proceed inefficiently. Multiple factors influence the outcome. As a result, metallicity alone cannot always reveal a galaxy's true history. Researchers must consider a broader context. That lesson continues influencing modern astronomy. Another important insight involves the role of dwarf galaxies. For much of the 20th century, public attention focused primarily on giant galaxies, the Milky Way, the Andromeda Galaxy, massive elliptical systems containing trillions of stars. These giants are undeniably impressive, yet dwarf galaxies may hold some of the most important clues about cosmic history. There are vastly more dwarf galaxies than giant galaxies. Many preserve characteristics lost in larger systems. Their simpler structures make certain evolutionary processes easier to study. In some respects, dwarf galaxies function as living archives, not because they remain unchanged, because they often evolve differently. I Zwicky 18 highlighted that value beautifully. A small galaxy became one of the most important laboratories for studying primitive conditions. Size turned out to be irrelevant. Scientific significance came from the information preserved inside the system. Perhaps the most fascinating lesson concerns time itself. Human beings naturally think of age as a straightforward concept. Something old looks old. Something young looks young. The universe does not always cooperate with that intuition. Galaxies complicate the relationship between age and appearance. A galaxy can possess ancient stars while maintaining youthful characteristics. It can look primitive despite surviving for billions of years. It can preserve conditions associated with earlier cosmic eras. I Zwicky 18 forced astronomers to separate two ideas that often become confused: chronological age and evolutionary age. Chronologically, the galaxy is old. Evolutionarily, it appears younger than many of its peers. That distinction changed how researchers think about galactic development. The implications extend even further. Once astronomers accepted that galaxies can evolve at dramatically different rates, another question naturally emerged. If I Zwicky 18 exists, what else might exist? Could there be other galaxies hiding in the universe that evolved unusually slowly? Could some systems be even more primitive? Could others preserve characteristics we have not yet encountered? The possibility is difficult to ignore. After all, astronomy repeatedly teaches the same lesson. Whenever researchers think they understand the full range of cosmic diversity, the universe produces another surprise. The discovery of exoplanets provided one example. Before the 1990s, astronomers had never confirmed a planet orbiting another Sun-like star. Today, thousands are known. Many possess characteristics nobody predicted. The discovery of dark energy provided another example. Few researchers expected it. Yet observations revealed it anyway. The universe consistently demonstrates a remarkable capacity for surprising its observers. There is no reason to assume galaxies should be different. In fact, recent discoveries suggest the opposite. Modern telescopes continue identifying unusual systems. Some possess extraordinarily low metallicities, others exhibit unexpected star formation histories. Still others challenge assumptions about structure, mass, or chemical composition. Every year brings new observations. Every year expands the known diversity of galaxies. This naturally raises an intriguing possibility. Perhaps I Zwicky 18 is not unique. Perhaps it is simply the most famous member of a larger family. Researchers have already identified several galaxies sharing certain similarities. None are identical. Each possesses its own history, its own environment, its own evolutionary path. Yet together they reveal an important pattern. Galactic evolution is more flexible than once believed. The universe allows multiple routes from beginning to maturity. Some routes are fast, others are slow, very slow. Could astronomers eventually discover a galaxy even more primitive than I Zwicky 18? The answer is almost certainly yes. Whether that galaxy exists nearby or at enormous distances remains uncertain. The universe contains hundreds of billions of galaxies, possibly trillions. Humanity has studied only a tiny fraction of them in detail. The search has barely begun. This is one reason new telescopes generate so much excitement. Every increase in observational capability expands the range of possible discoveries. The James Webb Space Telescope has already begun revealing galaxies from astonishingly early periods of cosmic history. Many of these systems appear different from what researchers expected. Some seem surprisingly mature, others display unusual characteristics. The data continue arriving. The surprises continue arriving as well. Future observatories will push even farther. Larger telescopes, more sensitive instruments, better detectors. Each generation will examine galaxies invisible to previous technology. Among those discoveries may be systems even more unusual than I Zwicky 18. Galaxies preserving conditions closer to the early universe, galaxies with even lower metallicities, galaxies following evolutionary paths not yet imagined. Astronomers fully expect such discoveries. The only uncertainty involves timing. Meanwhile, I Zwicky 18 continues serving as a bridge between theory and observation. The galaxy occupies a special position, close enough for detailed study, unusual enough to challenge assumptions, primitive enough to illuminate ancient conditions. Researchers return to it repeatedly because it remains useful. Every improvement in observational technology reveals new details. Every improvement in theoretical modelling provides new questions. The galaxy's scientific story remains unfinished. And perhaps that is the most important lesson of all. Science rarely ends with a final answer. Instead, answers become starting points. The original mystery asked whether I Zwicky 18 was the youngest galaxy in the universe. Astronomers eventually concluded that it was not. Yet that conclusion did not diminish the galaxy's importance. It increased it. The discovery led to better questions. Why did the galaxy evolve so slowly? How do primitive conditions persist? What controls the pace of galactic development? How many other galaxies follow similar paths? Each question opened new areas of research. Each question connected a small dwarf galaxy to much larger issues in cosmology. Today, I Zwicky 18 stands as something more valuable than the youngest galaxy candidate. It stands as evidence that cosmic evolution is not a race with a single finish line. Different galaxies reach different destinations at different speeds. Some mature rapidly, some take their time, and somewhere among the hundreds of billions of galaxies scattered throughout the observable universe, there may be other systems still waiting to challenge everything astronomers think they know. The search for those systems continues. Because every time humanity discovers an object like I Zwicky 18, the universe reminds us that its history is far richer, more diverse, and more surprising than any simple theory could ever predict. Somewhere in the darkness, about 59 million light-years from Earth, I Zwicky 18 continues exactly what it has been doing for billions of years. Stars are forming, gas is moving, radiation is spreading through enormous clouds of hydrogen. Gravity is quietly shaping the future of the galaxy one orbit at a time. Nothing about the system knows that human beings have spent decades debating its age. Nothing about the galaxy knows that it became famous. Nothing about it knows that thousands of scientific papers, observations, simulations, and discussions have revolved around its unusual characteristics. The galaxy simply exists, and perhaps that is the perfect place to begin our final reflection. Because throughout this journey we have been talking about age, young stars, old stars, young galaxies, ancient galaxies, cosmic history, evolution across billions of years. Yet the deeper astronomers investigated I Zwicky 18, the more they discovered that age is not always as straightforward as it first appears. At the beginning of the story, the mystery seemed simple. Astronomers found a galaxy with extraordinarily low metallicity. They found active star formation. They found an object that looked remarkably primitive compared with many nearby galaxies. The possibility immediately captured attention. Perhaps this was the youngest galaxy in the universe. Perhaps it had formed long after most galaxies had already completed much of their development. It was a bold idea. The kind of idea that appears in headlines. The kind of idea that inspires excitement. And for a while, the evidence seemed to support it. Then came better observations, better measurements, better telescopes. The Hubble Space Telescope revealed ancient stars. Researchers found evidence that the galaxy possessed a much longer history than originally suspected. The galaxy was not newly born. It was not a cosmic infant. It had existed through billions of years of cosmic evolution. Yet the story did not end there. In some ways, that discovery marked the true beginning, because now astronomers faced a more subtle mystery. How could an old galaxy look so young? The question forced researchers to rethink assumptions. Not assumptions about the age of the universe, not assumptions about gravity, not assumptions about cosmology itself. Instead, it challenged assumptions about how galaxies grow and change over time. Human beings naturally expect age and appearance to move together. A very old tree often looks old. A very old building often looks old. A very old city often contains visible signs of its history. Galaxies do not always follow the same pattern. Some mature rapidly, some mature slowly. Some preserve characteristics that seem strangely out of place in the modern universe. I Zwicky 18 became one of the clearest examples of that reality. The galaxy taught astronomers that evolution is not a race with a single timetable. The universe does not issue identical schedules. Different galaxies receive different histories, different environments, different opportunities, different challenges. The result is diversity, an enormous diversity that continues surprising researchers today. Perhaps that lesson extends beyond astronomy. When people think about history, they often imagine progress occurring at the same speed everywhere. Yet human civilizations develop differently. Languages evolve differently. Cultures evolve differently. Cities evolve differently. Nature appears to favor variety rather than uniformity. The universe seems to operate according to the same principle. I Zwicky 18 reminds us that there is more than one way to grow, more than one way to evolve. More than one path through cosmic history. That realization helps explain why the galaxy remains important despite no longer being considered genuinely young. In fact, its scientific value may be greater now than it was when astronomers thought they had discovered a newborn galaxy. A truly young galaxy would have answered one question. An old galaxy that behaves like a young galaxy answers many. It teaches researchers about star formation. It teaches researchers about chemical evolution. It teaches researchers about hydrogen reservoirs. It teaches researchers about the enormous variety of galactic histories. Most importantly, it provides a nearby laboratory for studying conditions that may resemble those found much earlier in the universe. That role becomes increasingly valuable as astronomy enters a new era. The launch of the James Webb Space Telescope transformed the study of distant galaxies. For the first time, astronomers began observing galaxies that existed astonishingly close to the beginning of cosmic history. Many of those observations created new puzzles. Some galaxies appeared larger than expected. Some appeared more evolved than expected. Some challenged theoretical predictions. Each discovery expanded humanity's understanding of the early universe. Yet every distant observation comes with limitations. The galaxies are incredibly far away. Their light is faint. Details remain difficult to resolve. This is where objects like I Zwicky 18 become essential. They provide nearby points of comparison. Researchers can study them in extraordinary detail. They can examine their stars, their gas, their chemistry, their structure. The galaxy effectively serves as a bridge connecting the nearby universe to the distant past, and that bridge continues attracting attention. Even today, astronomers are still learning from I Zwicky 18. New observations continue. New analyses appear. New models are tested. The galaxy remains a living scientific laboratory, not because it changes dramatically from year to year, because our ability to study it continues improving. Every generation of telescopes sees more than the previous one. Every generation of instruments reveals details that were once invisible. That pattern has repeated throughout the history of astronomy. There is every reason to believe it will continue. Some future telescope may uncover evidence nobody currently expects. Another instrument may identify similar galaxies. An entirely new class of primitive systems may eventually emerge. History suggests that such surprises are likely. After all, the universe has a remarkable habit of exceeding expectations. Astronomers repeatedly discover things they never anticipated. Black holes were once theoretical curiosities. Exoplanets were once unconfirmed possibilities. Dark energy surprised nearly everyone. Fast radio bursts arrived without warning. The universe continues revealing new phenomena whenever technology advances. There is no reason to believe the exploration of dwarf galaxies has reached its conclusion. Quite the opposite. The story may only be beginning. And that brings us back to one final question. Could there still be genuinely young galaxies waiting to be found? The honest answer is that nobody knows. Astronomy rarely deals in absolute certainty. The observable universe contains hundreds of billions of galaxies, possibly trillions. Humanity has examined only a fraction of them in detail. Many remain undiscovered, many remain poorly understood. Some almost certainly possess characteristics unlike anything currently known. Whether one of those galaxies is genuinely young remains an open question. Researchers generally expect such systems to be extremely rare. The universe has had nearly 14 billion years to build galaxies. Most should have begun forming long ago. Yet astronomy has taught scientists to be cautious about declaring something impossible. Rare is not impossible. Unlikely is not impossible. The universe has earned the right to surprise us. For now, however, I Zwicky 18 occupies a special place. Not as the youngest galaxy. Not as the oldest galaxy. Not as the largest or brightest galaxy. Instead, it stands as a reminder that appearances can be misleading. A reminder that history is often more complicated than first impressions suggest. A reminder that cosmic evolution follows many different paths. Perhaps that is why the galaxy remains so memorable. Its story began with a misunderstanding. Astronomers thought they might have found a newborn galaxy. Instead, they found something arguably more interesting. A galaxy that refused to age the way researchers expected. A galaxy that preserved clues from earlier eras. A galaxy that transformed a simple question into a much deeper one. And that deeper question concerns time itself. Not time measured by clocks, not time measured by calendars. Cosmic time, the immense timeline stretching from the Big Bang to the present day. Within that timeline, billions of galaxies have lived billions of different lives. Some changed rapidly, some changed slowly, some vanished, some merged, some evolved into structures so large they contain trillions of stars. Others remained small, quiet, unusual. I Zwicky, 18, belongs to that second group. A small galaxy that became important because it did not follow expectations, because it preserved secrets, because it reminded astronomers that the universe is more creative than any model. And perhaps there is something comforting about that. Even after centuries of scientific progress, the cosmos remains capable of surprise. Questions remain unanswered, mysteries remain unsolved. Entire discoveries still wait beyond the reach of current instruments. The night sky is not a completed map. It is an unfinished investigation. Every telescope expands the search. Every observation adds another piece to the puzzle. And somewhere among the countless galaxies scattered across the observable universe, other stories are waiting. Other mysteries, other surprises, other objects that will challenge assumptions and reshape understanding. For tonight, however, our journey ends with a small dwarf galaxy that taught astronomers an unexpectedly large lesson. Not about youth, not about age, but about the difference between the two. Because in the end, I Zwicky 18 revealed that growing older and growing up are not always the same thing, and on the scale of the universe, that distinction may be one of the oldest secrets of all.